शुभं कुरु त्वं कल्याणम् आरोग्यं धनसम्पदः शुभं कुरु त्वं कल्याणम् आरोग्यं धनसम्पदः शत्रुबुद्धिविनाशाय दीपज्योतिर्नमोऽस्तुते दीपज्योतिर्नमोऽस्तुते दीपज्योतिर्परब्रह्म दीपज्योतिर्जनार्दनः दीपज्योतिर्परब्रह्म दीपज्योतिर्जनार्दनः दीपो हरतु मे पापम् सन्ध्यादीपनमोऽस्तुते ओ दीप ब्रह्मरूपस्त्वं ज्योतिषां प्रभुरव्ययः ओ दीप ब्रह्मरूपस्त्वं ज्योतिषां प्रभुरव्ययः आरोग्यं देहि पुनश्च पतिं स्वच्छामि मे सदा रवेरस्तं समारभ्य यावत् सूर्योदयो भवेत् रवेरस्तं समारभ्य यावत् सूर्योदयो भवेत् यस्य तिष्ठे गृहे दीपः तस्य नास्ति दरिद्रता शुभं कुरु त्वं कल्याणम् आरोग्यं धनसम्पदः शुभं कुरु त्वं कल्याणम् आरोग्यं धनसम्पदः शत्रुबुद्धिविनाशाय दीपज्योतिर्नमोऽस्तुते दीपज्योतिर्नमोऽस्तुते शुभं कुरु त्वं कल्याणम् आरोग्यं धनसम्पदः शुभं कुरु त्वं कल्याणम् आरोग्यं धनसम्पदः त्वं कल्याणम् आरोग्यं धनसम्पदः शुभं कुरु त्वं कल्याणम् आरोग्यं धनसम्पदः शत्रुबुद्धिविनाशाय दीपज्योतिर्नमोऽस्तुते दीपज्योतिर्नमोऽस्तुते दीपज्योतिर्परब्रह्म दीपज्योतिर्परब्रह्म दीपज्योतिर्जनार्दनः दीपो हरतु मे पापम् सन्ध्यादीपनमोऽस्तुते ओ दीप ब्रह्मरूपस्त्वं ज्योतिषां प्रभुरव्ययः ओ दीप ब्रह्मरूपस्त्वं ज्योतिषां प्रभुरव्ययः आरोग्यं देहि पुत्रांश्च पतिं स्वच्छां हि मे सदा रविरस्तं समारभ्य यावत् सूर्योदयो भवेत् रविरस्तं यस्य तिष्ठे गृहे दीपः तस्य नास्ति दरिद्रता शुभं कुरु त्वं कल्याणम् आरोग्यं धनसम्पदः शुभं कुरु त्वं कल्याणम् आरोग्यं धनसम्पदः शत्रुबुद्धिविनाशाय दीपज्योतिर्नमोऽस्तु ते दीपज्योतिर्नमोऽस्तु ते शुभं कुरु त्वं कल्याणम् आरोग्यं धनसम्पदः शुभं कुरु त्वं कल्याणम् आरोग्यं धनसम्पदः गणनायकाय गणदैवताय गणाध्यक्षाय धीमहि
A very good morning to everyone. I am Dr. Swarnalatha, Professor, Department of Pharmaceutical Chemistry, Mahathi College of Pharmacy, Madanapalle, Chittoor District, Andhra Pradesh. On behalf of Mahathi College of Pharmacy, I wholeheartedly welcome all principals, teaching faculty, my dear students, and distinguished participants across the country except few states to the webinar titled Novel Insights in Antimicrobials and Analytical Techniques by two great renowned professors who are very much familiar in pharmacy education, who have graciously consented to share their insights in the chosen topics. I strongly believe that this webinar will ignite our minds on the chosen subject and ultimately will yield in acquiring in-depth knowledge and understanding the subject in right perspective. The webinar is under live stream through YouTube channel. Further, the college has facility of campus radio. The webinar content will be broadcasted through our college radio. The interested participants can download Unify app from App Store, and by clicking Mahathi College of Pharmacy, you can utilize the opportunity of hearing the subject matter again. Without delay, I take opportunity to introduce distinguished speakers, though the speakers do not require any introduction as they are familiar with their vast knowledge. It's my privilege to introducing these few lines. Now, I welcome today's speaker, Professor N. Sankaraya Garu, Associate Professor HOD, Department of Medicinal Chemistry, Naipur, Hyderabad. He received undergraduation and post-graduation degree in chemistry from Kakatiya University. He completed his PhD in 2007 at CSIR Indian Institute of Chemical Technology, Hyderabad. He received Young Scientist Award 2010 from Mumbai, Best Scientist Award 2016 from Naipur, Hyderabad. His credit, he published 105 research papers in national and international journals, including patents. He is going to deliver the topic, the role of NMR spectroscopy in structure elucidation. Thank you, sir. Hand over to Sankaraya, sir.
Can introduction? Can you hear me? So can you hear me? Hello? So very good morning, all of you. So at outset, I must thank the organizers, that is Mahathi College of Pharmacy. Especially, I thank the chairman, so Mr. Ramanath Reddy and Dr. P. Shantil Kumar, director, and Dr. Lakshmi Narasimhaya, principal, and who has contacted Vinay. So I very much thankful to all of you, and especially the participants, faculty friends, and the speaker Dr. Reddy Shetty, Prakasham from Chief Scientist from IICT. So I welcome you all for this my talk. So I will give a brief overview of the role of NMR spectroscopy in structural isolation of organic molecules. So I will give like a brief overview of theory. So what are the historical perspective of this NMR spectroscopy, and what are the signals, how they split into multiple peaks, and then what are the coupling constants, and we can calculate the coupling constants, and what is the topicity of NMR, and how we can convert complex spectra to simple spectra. So those things I will cover in detail, and also I will cover a little about carbon-13 NMR spectroscopy and depth, and there's some of the applications. So these are the suggested reading books. So what is NMR spectroscopy? So the NMR spectroscopy is the study of molecular structure through the measurement of an oscillating radio frequency of electromagnetic radiation with a collection of nuclei in the presence of strong electromagnetic field. So it means, so you are keeping by using NMR measures the absorption of electromagnetic radiation in the radio frequency region, that is especially for 4 to 900 megahertz. So in this absorption process, what is exactly is happening? So instead of outer electrons, the nuclei of certain atoms are involved in this absorption process. So you have to keep this sample need to be placed in a strong magnetic field to cause different energy states. So without this energy states, it's very difficult to study about the nature of the nuclei. So now the NMR spectrum can provide the detailed information about the molecular structure. Not only molecular structure, you can study about their dynamics of the particular molecules. If you see the historical perspective, exactly where NMR like a discovery has been started. So if you see very carefully, as we know, we studied about the Zeeman effect. So Professor Zeeman, he shared a Nobel Prize in 1902. So for discovering that certain atoms of nuclei behave strangely when subjected to strong magnetic field. So the Zeeman effect, you can see the pictorial diagram. It shows when mercury lamp at wavelength of 46.1 nanometers, the A you can see that is without magnetic field, B with magnetic field, and C with the Zeeman effect. You can see the signals, the effect of Zeeman splitting of a spectral line into several components in the presence of a static magnetic field. So means he has studied the certain atoms of the nucleus, how they are behaving in the strong magnetic field. When they are subjected to strong magnetic field, they behave strangely in the presence of magnetic field, in the absence of magnetic field, in the presence of magnetic field. So then that is the actually for the coin for the discovery of NMR. So as you know, nowadays the NMR has completely revolutionized the study of chemistry, biochemistry, chemical biology, and other disciplines. So later, the first time the NMR word coined by nuclear magnetic resonance coined by Professor Isaac Rabi from Columbia University, is first to measure the nuclear magnetic spin in lithium isotopes and protons, now which are using as a magnetic resonance image in the diagnostic centers. So he shared a Nobel Prize again in physics, 1944. So this is like a first NMR of water molecule in different time scales, T1, T2, T3, T4. So this is like a performed by, this experiment is performed by Felix Bloch from Stanford University. So again, two professors, Felix Bloch from Stanford University, Edward Purcell from Harvard University, both of them shared a Nobel Prize in 1952, again in physics, for putting the so-called nuclear Zeeman effect to practical use by constructing the first crude NMR spectrophotometer. So by using this the nuclear Zeeman effect principle, they first time they constructed a crude spectrophotometer, and you can see the ethyl alcohol the beginning of high resolution NMR, ethyl alcohol, you can see 3 peaks, like they are broad. They are not much resolution, but you can see the below same ethyl alcohol, modern ethanol spectra, how they are splitting CH3, CH2, OH, how they are splitted, and it's very clear. So this is like a first crude NMR they constructed in 1946, but they shared the Nobel Prize in 1952. And again, in chemistry, first Nobel Prize received in NMR in 1991 by Richard Ernest, where he has developed a methodology of high-resolution nuclear magnetic resonance spectroscopy and frontier transfer NMR, 2D NMR, nuclear over effect. Means not only the spin-spin interaction can take place through the intervening covalent bonds, but also it can take place, the spin magnetization can magnetization can take place from one spin path to another spin path through a spatial, that is called nuclear over effect. So he has first introduced so for the high resolution NMR. Again, 2002, Professor Kutuj from Switzerland, he received again Nobel Prize for the study of 3D biomolecular structures where proteins, peptides, alpha helices, beta helices, so their interactions, intermolecular hydrogen bond. So he has established for the 3D biomolecular structures by using NMR. And later again, two scientists, they received a Nobel Prize in medicine for the they awarded Nobel Prize for pioneering research in MRI and cellular channels. So then coming to the structural elucidation of organic molecules, how this NMR spectroscopy can employed for the structural elucidation. See, any single spectroscopy cannot give 100% of the complete structure of the molecule, as we know, because there are many spectroscopies are there. So there NMR, mass spectrometry, UV, IR, Raman spectroscopy, and ESR, electron spin resonance spectroscopy, microwave, IR. So these all combine only, you can go for like a structural elucidation. But any one of the spectroscopy cannot give X-ray crystallography that can give you 100% structural elucidation. But as we know, unfortunately, 90% of the organic compounds are not single crystalline compounds. They are maybe in the form of powder, they may be form of in the semi-liquids, they are form of liquids, some of them are in the gaseous. So that's why, though it is like a fantastic X-ray spectroscopy, but 90% of the compounds are not crystalline compounds. But you can see among the all the spectroscopies, but 70 to 80% of the structural information can be obtained from NMR. So what you can get from the NMR? So whether it's a proton or carbon-13 or fluorine. So if you take these which are magnetically active, those type of certain atoms of nuclei, their nature you can study by using radio frequency radiation. So the applications, if you see, the NMR can provide the complete information about the nature of the protons in the given samples, where that proton or carbon are located, whether it is attached to nitrogen or oxygen or sulfur, whether it is attached to sp3 carbon, sp2 carbon, or sp carbon. So you can exactly where it is exactly located, you can study. And also you can study about chemically non-equivalent sets of protons can be detected. So in a molecule, how many chemically equivalent, how many chemically non-equivalent sets of protons are present? So how many chemically non-equivalent sets of protons are present? So those many signals you can see in the spectra. Not only that, in chemically non-equivalent sets of protons, how many sets are present in the given molecule? That also you can see. And also you can see the environment of each set of protons and how many number of neighborhood protons are present. Not only that particular protons, you can see study about the neighborhood protons nature, whether it is how they are coupling each other. So you can study about the neighborhood protons. Not only that, you can see the diastereomeric nature of the proton, diastereomeric relationship of the protons, like cis-trans isomerism. Easily you can distinguish through the coupling constants of the certain molecules. So for example, interpreting NMR spectra, we will see first very simple examples, then we will go. So first, when you are looking into the NMR spectra, you have to see how many chemically equivalent, how many chemically non-equivalent sets of protons are present in a given molecule. Okay. So for example, if you see simple acetaldehyde, if you take this acetaldehyde, there are CH3, 3 protons are there. These 3 protons are chemically equivalent because they will give same chemical shift value. These 3 protons, because they are attached to sp3 carbon. So they are homotropic protons, we can call it as. So they will give singlet. and then one more proton is there, aldehydic proton, that is attached to sp2 carbon. So that is chemical environment is different. So here we are having two chemically non-equivalent sets of protons are present. So two chemically non-equivalent means you will get two signals in the spectra. As you can see, 2.1, one singlet 3 protons, another one is 9.9 singlet 1 aldehydic proton. So here you are having two chemically non-equivalent sets of protons are present. For example, you can see next example, 2-butene. In 2-butene, there is a CH3, CH, CH, CH3 is present. So two CH3 groups are there, and then two protons are attached to sp2 carbons differently. So here there is a symmetry in the molecule 2-butene. So here you will get two chemically non-equivalent sets of protons are CH3, CH3 chemically equivalent, and HH are chemically equivalent. So that's why CH3 but H are chemically non-equivalent. So here there is symmetry is present in this molecule. So that's why you will get only two chemically non-equivalent sets of protons are present. So as you can see, 6 protons are giving doublet and 2 protons are giving quartet. It's very clear. Chemical shift values are very clear. Splitting also very clear. Doublet and quartet. Next one, if you see N-propanol. So in N-propanol, so there are 4 chemically non-equivalent sets of protons are present, hydroxy 1 and CH2, CH2, CH3. As you can see, 4 peaks are there. TMS as a standard 0. So reference compound reference. So then remaining 3 protons, 2 protons, 1 OH and 2 CH2 protons, like a quartet, singlet, and sextate, and then triplet. So next, ethyl benzene. If you see ethyl benzene, phenyl groups are coming 5, like a 7.1 in the aromatic region, and the next one is triplet. Quartet is very clear, CH2, CH3. So this is like a very simple example. You have to see how many chemically non-equivalent sets of protons are present in a given molecule. Those many signals you can see in the spectra. This is like a fundamental knowledge to determine, because daily life we will keep some reactions one step to another step. So to predict the structure of the molecule, so you have to see how many chemically non-equivalent sets of protons are present. So those many signals you can obtain in the spectra. So next, what is the principle involved in this NMR? So just let us see with about the proton. So the proton is similar to carbon 13. Everything is same. The nature of the like nuclei. So for example, if you see the nature of proton, hydrogen atom nuclei is positive charged particle with 1 proton and 1 neutron. So if you see the natural abundancy, always this whether it is proton or carbon 13 or fluorine or whatever it is, so it is depending upon the natural abundancy of the that particular proton or carbon. So if you see the protium for proton, natural abundancy is 99.98%. Similar to an electron, the positive charge nucleus also undergoes spinning. What is spinning? Any particle moves around its own axis is called spinning. So while spinning, it will generate a magnetic field around it. But you keep in mind, all spinning nuclei may not generate a magnetic field. Which are magnetically active, those only can generate a magnetic field. So magnetically active, those only can generate the magnetic field. So which are magnetically active. So this spinning nuclei, there are two. It will depend on two physical properties. That is angular momentum, magnetic momentum. So these two physical properties again depend on the spin quantum number. If spin quantum number I is equal to 0, so it is magnetically inactive. It is not useful for the NMR. So if I is equal to not 0, so then it is whether it is integer value or non-integer value. So this is very important. It's magnetically active. Those are like useful for the NMR. So the spinning may be clockwise or anti-clockwise. So this is the formula to calculate the quantum values. So like a nuclear magnetic momentum, spin field interaction, magnetic field along z axis. So this is the principle. So for example, some example if you see sulfur 32, carbon 12, oxygen 16. If you see the spin quantum number of protons even, number of neutrons are even. So I value spin quantum number is 0, is equal. So it is magnetically inactive. So for example, if you take carbon 13 and oxygen 17, so then even number and odd number, so it is non-integer value. So remaining are, except first case, all are magnetically active. So you can see a model hydrogen nucleus spinning on its own axis. So the molecules are like a degeneracy state. So it is like a nucleus is a tiny magnet. So without magnetic field, so it is very difficult to generate a two energy levels. See here, if you want to study the nature of the nuclei, you want to study about the nature of nuclei. So here you require your sample and radio frequency radiation. But why you require strong magnetic field? See, in the absence of magnetic field, you see left side how their nucleus are degenerate state. They are moving randomly. They are moving randomly, and there is no field. As you can see, left side there is no field left, no magnetic field. They are in the random motion. So, but in the presence of magnetic field, you can see the right side. They are moving in a particular direction with respect to external magnetic field. So the magnetic field generate a two energy levels, low energy level, high energy level. So then they are moving in a particular direction, upward transitions, downward transitions by using radio frequency radiation. So the proton of nuclei from low energy level to high energy level, by absorbing this radio frequency radiation, the flipping can take place, nucleus flipping can take place. So then when you are giving radio frequency pulses, when you stop, then again it fall into the ground state. So by releasing the energy, that it will come in the form of a signal. So when you are applying external magnetic field, so some of the proton nuclei align to the external magnetic field, that is low energy level, or parallel direction to the applied magnetic field. Some of the nucleus opposed, anti-parallel to the direction of external magnetic field, that is beta level. Low energy level we can call it the alpha level, and high energy level we can call it as a like a beta level. So in the presence of magnetic field, these two energy levels will be there. So then when you are applying radio frequency radiation, it will absorb the that nucleus, certain atoms of nucleus absorb the radio frequency radiation, and flipping can take place, then resonance can take place. So this is obviously depending upon the, in the strong magnetic field, this any molecule, certain atoms of nucleus, they have some their own like frequency, like a spinning nature. So like a precision in the presence of strong magnetic field. So in the precisional frequency, this entire NMR principle works through the precisional frequency of certain atoms of nuclei. What is precisional frequency? In a given time, the number of rotations performed by a spinning nucleus in the direction of external magnetic field is called precisional frequency, that we can symbolize with nu L. So this precisional frequency, again, it's depending upon the how much external magnetic field you are applying, that is B0 or H0. So that B0 or H0 you can measure in Teslas. How much Tesla of like external magnetic field you are applying. For example, 1.41 Tesla you are applying, that is equal to 60 megahertz precisional frequency. So this precisional frequency, first time Professor Larmor is like used this identified this precisional frequency. That's why we can call it a Larmor frequency. So this precisional frequency we can measure in cycles per second or hertz or megahertz. So again, this precisional frequency is depending upon three factors. One is external magnetic field. If external magnetic field increases, the precision frequency also increases. It's like a directly proportional. And number two, electronegativity and electron density. If electronegativity increases, precision frequency increases. And again, electron density increases, precision frequency decreases. Because the for example, some of the molecules are, if they are having a more density of electrons, like tetramethylsilane, you can take as a reference. We are taking tetramethylsilane. So that is like a 4 CH3 groups are there, that highly densile. What happens when you are applying external magnetic field? So already they have a lot of density. So then the precision, they generate secondary magnetic field. That secondary magnetic field oppose the external magnetic field. So the net magnetic field reduces. That's why they will give a very less chemical shift value. If that's why it's like a precision frequency and electron density inversely proportional. But electron density, electronegativity is directly proportional. And next one is gyromagnetic ratio, third one. So the gyromagnetic ratio, for example, this is depending upon the natural abundancy. For example, if a proton, if you see 99.9% natural abundancy, but if you see carbon-13, only 1.1% of natural. That's why the gyromagnetic ratio is 4:1 when you compare to proton and carbon-13. Next, what is resonance? Because there is nuclear magnetic resonance. What is resonance? So resonance is the absorption of energy by a precessing nucleus and the resulting flip of its nuclear spin from low energy state to a high energy state. So the precessing spin induces the oscillating magnetic field that is recorded as a signal by the instrument. So that's why we are using strong electromagnetic field. So because the protons of nuclei are they move in a particular direction. So then you can easily study about the nature of the certain atoms of nuclei. So means you are measuring the oscillating magnetic field that is for coming as a signal. So it's upward transitions, downward transitions. Next one is, so how much electromagnetic field you are applying, how much, for example, you are applying 1.41 Tesla. If you are applying external magnetic field, that is equal to 60 megahertz. If you are applying 2.35 external magnetic field, that is equal to 100 megahertz frequency. And 11.75, it is a 500 megahertz. So the resonance condition should be matched. Otherwise, the signal cannot be generated. So if you increasing the external magnetic field, the separation between the alpha and beta level, energy separation also increases. When energy separation increases, you require more radio frequency radiation. So these both conditions must be matched. Then only the signal can be generated. And also in this, the saturation in NMR is not good. Saturation in NMR means always the proton nucleus or whatever it is, carbon 13 nucleus or proton nucleus, always they are populated at alpha level is more than that of the beta level, because alpha level is more stable because it is the ground state. So that's why the always the population, but the amount of this population difference is very minimal. So that can be seen through the Boltzmann calculations. So this NMR spectrometer layout. So if you see, this is like a these are two powerful electromagnets, that is superconducting electromagnets. They are cooled at minus 80 degrees centigrade. So through liquid helium and liquid nitrogen, always in 365 days it should be live, whether you are using or not. So this radio frequency input oscillator, this is sample tube, radio frequency output receiver, and this will come as a signal. So this is like a particular typical layout of this nuclear magnetic resonance spectrophotometer, where you can see this sample here, sample tube inside. It looks like this. So the sample is dissolved in deuterated like solvents. You have to keep here, and then the superconducting magnet. This is the NMR probe, and this is NMR console, and this is the computer putting these signals together, and you will get in the form of signal. So this superconducting magnets in modern NMR spectrometers have coils that are cooled in liquid helium and conduct electricity with essentially no resistance. So that's why we have to use. This is the only main like a disadvantage of NMR, because always you have to keep it in minus 80 degrees centigrade, and 365 days you have to keep it in live. Otherwise, demagnetization can take place. So then we will see what is chemical shift. So the difference in absolute precision frequency of sample protons and absolute precision frequency of reference protons, and in the presence of instruments in megahertz, because the chemical shift should be field independent. Whether you are performing 60 megahertz or 100 megahertz or 500 megahertz, you have to get same chemical shift value. By using this delta, this principle, you will get the same, because it is like a this principle gives the field independent chemical shift values. So this is like, for example, if you see 60 megahertz, same chemical shift values from 0 to 10, but precision frequency increases. When you are applying external magnetic field from 60 megahertz to 100 megahertz, if you see at 300 megahertz, the precision frequency increases, but the chemical shift values are same. It's like a field independent. So the chemical shift values are for the proton NMR from 0 to 18. Okay, so where you will get like aliphatic system from 0 to 2, and where this sp3 carbon protons are attached to carbonyl carbon, you will get 2. Even aromatic ring also you will get 2.1, 2.2, and halogen OCH3 groups you will get 3.8 to 4.2. Nitrogen attached 3.5 you will get it, and then olefinic ethylenic protons you will get from 5 to 6.5, aromatic protons you will get 7 to 8, and aldehydic proton 9 to 10, carboxylic protons from 10 to 12. Intramolecular hydrogen, for example, if you take orthohydroxybenzaldehyde, that intramolecular, due to intramolecular hydrogen bonding, so that OH will come 13 to 14. If, for example, if you take ethyl esteoestate, keto-enol tautomerism, you can see through intramolecular hydrogen bonding in enol, that particular proton will come even 17 to 18 due to chelation or intramolecular hydrogen bonding. So depending upon where that protons are located. So then why we have to see why these different chemical shift values are, what are the factors are influencing on chemical shift values. Those also we have to see. It's very, very important why these particular functional groups are giving different chemical shift values. And next, if you see the same carbon 13, that is coming 0 to 220, the chemical shift value, same functional groups. So these are the different functional groups. Just you can download from the, you can refer the textbook, or you can download from the chemical shift values from the internet. And please remember this approximate values of the chemical shift values. These, if you know average values of these chemical shift values of all functional groups from like alkanes, alkynes, and different hydroxy compounds, alkyl halides, alcohols, amines, primary, secondary, and then aromatic compounds. So if you know these certain values ranges, then it's very easy to distinguish in the structural elucidation of the unknown compounds. So these are the different chemical shift values of certain functional groups. And what are the factors influencing on chemical shift values? There are three factors: electronegativity of atom attached to proton, van der Waals effect, and anisotropic effect. So due to these factors, they are giving different chemical shift values. For example, electronegativity is directly proportional to the chemical shift values, and electron density is inversely proportional to the chemical shift values. So as we know, the electronegativity is directly proportional to the precision frequency. Precision frequency is directly proportional to the chemical shift values. If precision frequency is more, you will get more chemical shift values, but electron density only inversely proportional. For example, in this molecule, if you see tetramethylserine as 0 as a reference, if you take methyl iodide 2.16, when it is come to methyl fluoride 4.26 chemical shift value. Why? Because fluorine is more electronegativity than chlorine, bromine, and iodine. So here what happened? This fluorine is highly electronegative atom. It withdraws the electrons by inductive effect. So then obviously that particular CH3 group, the electron density is less, because this fluorine is attracting the electrons. It is withdrawing from the CH3 group. So obviously the electron density is less. When electron density is less, precision frequency is more. Precision frequency is more, chemical shift values are more. That's why you are getting 4.6, because fluorine is highly electronegativity atom. Next, van der Waals deshielding. When protons in a rigid molecule, if you see, when the protons are located in sterically hindered position, so due to this electrostatic repulsions and due to hindering groups, so the most of the protons are deshielded. So then when it is deshielded, you require lesser amount of applied magnetic field will be sufficient to bring such hindered proton into resonance. So the sterically hindered protons appear at higher chemical shift values. For example, tertiary proton, if it is surrounded by 2-3 CH3 groups, so that particular proton will give you more chemical shift value than the CH3 or CH2 protons. Next, third one is anisotropic effect. What is anisotropic effect? If you see isotropic effect, any effect which distributes in the molecule uniformly, means all parts of the molecule, if it is uniform, that effect, so that is called isotropic effect. But any effect which distributes non-uniformly in the molecule, that is called anisotropic, means it will only peri-peri effect will be there, not the whole molecule. That is called anisotropic effect. So in the presence of magnetic field, so it will generate secondary magnetic field. Some of the molecules like which are having 5 bonds containing molecules, they possess secondary magnetic field because they have their own 5 electrons. So due to this external magnetic field, the 5 electrons rotate further and they will generate secondary magnetic field. That secondary magnetic field not uniform in the molecule. So some of the there it is diamagnetic and paramagnetic. if the protons are in the paramagnetic, they have more chemical shift values than the diamagnetic. So this anisotropic effect of magnetic field on a proton in paramagnetic region is more when compared to diamagnetic region. So therefore, the crystal frequency is paramagnetic region is always more than that of the diamagnetic region. For example, you can see there is like a discrepancy in when you compare with like ethylene and acetylene. So as you know, the electronegativity increases. Electronegativity increases like sorry, when S character is increases, electronegativity increases. So when compared to sp3 hybridization, sp to sp, so sp is 50% character of the S character. So obviously the sp carbon dioxide protons having more electronegativity than the sp3. So theoretically sp protons should have more chemical value than the sp2 protons like ethylenic protons. But when experimentally they have seen sp2 ethylenic protons are giving more chemical value than the ethylenic proton. So this can be explained very well through anisotropic effect. So what happened? For example, if you see ethylene, so ethylene when exposed to strong electromagnetic field, so it will move perpendicular direction to the external magnetic field. So this ethylene is having 5 electrons. So they orient, they further rotate, and it will generate secondary magnetic field. That secondary magnetic field is non-uniform in the molecule. Like peri, the protons are left and right side. The protons are in the paramagnetic region and remaining is diamagnetic region. So that's why protons are in the paramagnetic region. They are more chemical value than the diamagnetic. So this induced local magnetic field of the 5 electrons reinforces the applied field at the hydrogen atoms. So it requires higher frequency radiation to bring a vinylic hydrogen nucleus into resonance. That's why these ethylenic protons will give you like a 5.5 to 6.5 when compared to. Then we will see the acetylene. So when acetylene is exposed to the strong magnetic field, it moves parallel direction. It moves parallel direction to the applied magnetic field. But here the acetylenic protons are in the diamagnetic region. That's why they will give less chemical shift value when compared to ethylenic protons. Similarly, if you see benzene, so in benzene also all 6 protons are sp2 carbon dioxide protons. So they are also like ethylenic protons, but ethylenic protons are giving 5.5 to 6.5. But benzene like aromatic protons are giving like a 7 to 8.5 chemical shift values. Why they are giving more chemical shift value when compared to ethylene? So here when benzene like aromatic compounds like exposed to strong magnetic field, so already the benzene is having 3 5 electrons. The 3 5 electrons already they are rotating. But when you are applying strong electromagnetic field, they further rotate and they will produce substantial ring current. So due to this ring current, so they will give more chemical value than the ethylene because there is a delocalization of the 5 electrons and they produce substantial ring current. So and in benzene also these all 6 protons are in the paramagnetic region and that's why they are giving more chemical value. And similarly, if you see aldehydic proton that is giving 10 to 12. Why they are giving 10 to 12? Because that is also like a ethylene C double bond OH. So there two, one is anisotropic effect and another one is oxygen electronegativity effect. That's why due to these both effects, so it's coming 10 to 9 to 10 the chemical sheet values of aldehyde. And carboxylic groups they are giving 10 to 12 because OH, 2 oxygens are present and anisotropic effect. Due to that, this most of this anisotropic effect you can see in 5 bonds containing molecules like alpha pinene, 18 aniline. Even the protons are located inside, they will give negative chemical shift values because the protons are located in diamagnetic region. And next, not only this 5 bonds containing, for example, if you take cyclohexane, so in this cyclohexane also you can see some anisotropic effect. So which are sigma bonds containing molecules. So here equatorial protons are in paramagnetic region, axial protons are in diamagnetic region. So there is a 0.03 chemical shift value difference for axial and equatorial protons at lower temperatures. Next, okay, we have seen what are the factors are influencing on chemical shift values, why each different functional groups are giving different chemical shift values, that also we know. So the factors also, one is electronegativity, electron density, anisotropic effect, and van der Waals effect. So these are the factors are like affecting on chemical shift value. That's why you are getting different chemical shift signals you are getting, or peaks you are getting. Next, okay, we have got these signals, why they are giving different chemical shift values, we know. Then the signals, why they are splitting into multiple peaks. So the spin-spin interaction or spin-spin coupling. So that is like a simple, the cleavage of NMR signal or peak in NMR spectrum is called spin-spin splitting or spin-spin interaction or spin-spin coupling. So these peaks are split into multiple peaks. Why they are giving multiple peaks? Due to magnetic interaction between non-covalent protons on adjacent carbons. The process is called as a spin-spin splitting. How this spin-spin splitting can take place? Because there is a intervening, because for example, if you take geminal means two protons are attached to same carbon, vicinal neighboring 1-2 protons. So this spin-spin interaction can take place through the intervening covalent bonds. This is like a true couplings. So this spin-spin magnetization, polarization can take place from one position to neighborhood protons. Not only attached protons, it will go to the neighborhood protons. Then spin-spin interaction can take place. Then the single peak, depending upon the neighborhood protons, it will split into multiple peaks. So this spin multiplicity, the number of lines which are associated with NMR peaks or lines is known as multiplicity. If it is singlet, one line, singlet, two lines, doublet, triplet, quartet, this all well known for you. So this also go through the Pascal triangular method, singlet, doublet, triplet. So it's just like they cannot split, there is a intensity, they will follow this Pascal triangular method. And how this origin of the signal splitting can take place? When 2 chemically non-equivalent, when 3 chemically non-equivalent, when 4 chemically non-equivalent sets of protons are present, how they are like a spin-spin interaction can take place. That we can see in proton NMR. For example, if you see here, 2 chemically non-equivalent sets of protons are present, HA and HB. So this HB is interacting with HA, means plus of, and again HA also interacting with HB, minus of. So means plus of, minus of, upward transition, downward transition, where 2 chemically non-equivalent sets of protons are present. So upward transition plus of, downward transition minus of. So it is giving doublet. HA is giving doublet because HA is giving doublet because the HB is interacting with HA. So 1 plus 1, 2, doublet. Spin multiplicity. For example, again here HA again interacting with HB, and upward transition and downward transition. Even HA also giving, HB also giving doublet. So because they are mutually interacting each other, that's why the HA also giving doublet, even HB also giving doublet. Next, the first one we have seen HA and HB. When 2 chemically non-equivalent sets of product, when for example HA and HBB, you can see. So this is M plus 2 means 3 triplet. You have to get it as per the spin multiplicity. So this HA is interacting with HB. Again, this is above HB, and HB both are chemically equivalent. HB. This HB also interacting with HA. So this HB will give you doublet, but HA will give you triplet. So as you can see, triplet spin multiplicity, because 2 chemically non-equivalent sets are there. So 2 are upward transition, and 1 is upward, 1 is downward, 1 is downward, 1 is upward, that is 2, and then 2 are downwards. So you will not get more than this spin multiplicity possibilities. So this is very clear, 1 is to 2 is to 1. And similarly, 3 chemically non-equivalent sets of atoms. So you can see 3 equivalent HB atoms are there, HB. So this HB will give you doublet with HA, but HA will give you quartet. See, 1 is to 3 is to 3 is to 1 ratio. So this is like a splitting pattern of the protons. For example, you can take typical example 2 pentanone. It's like a symmetrical molecule because this CH2CH3 and the left side also CH2CH is like a symmetrical molecule. So here 2 chemically non-equivalent sets of protons are present, that is CH2 chemically equivalent, and CH3 at the end chemically equivalent. So 2 chemically non-equivalent sets of protons are present. So you will get quartet and triplet. So you can see expanded spectra, quartet 4 lines and triplet 3 lines as per the Pascal triangular method they are splitting is, the intensities are very accurate. And so this is like a 2-pentanone, how they are splitting each other. Then we can see more complex splitting pattern of ethyl 1 propionate. So here this OCH2CH3 De, which is like denoted D and E, CH2CH3. So this D is protons are, this CH2 is attached to oxygen OCH2. So due to this electronegativity is giving 4.2 chemical shift values due to electronegativity effect. So neighborhood 3 protons are there. So as per this field multiplicity principle, you are getting 1 plus 3, 4 means quartet. You will get the quartet D. And then CH3 is giving triplet because neighborhood 3, 1 plus 2. So 3 means triplet. So this is very clear. Quartet triplet. It's very clear. If any molecule, if you see the spectra, if any quartet triplet is there, if their coupling constants are same, so then you can directly can take there is a CH2CH3 system is present in that given molecule. You can easily recognize. And next one, the complexity is ABC, this splitting pattern, because there is a double bond. Okay, so here you can see a little bit complex splitting. So it's very easy. If you see A and B, there is a trans relation, and C and B, cis relation. Okay, the A and C are attached to the same carbon, sp2 carbon. Like these two, A and C are geminal protons, right? Because they are attached to same carbon. But these A and C protons are chemically non-equivalent. Though they are attached to same carbon, they are chemically non-equivalent because the HA and HB are trans relation, okay, and HC and HB are cis relation. So this HB is differently coupling with HA and with trans relation. B is coupling with HC with cis relation. That's why this HB is giving doublet of doublet. As you can see, B doublet of doublet, and HA is giving with HB trans coupling doublet, and HC is coupling with HB doublet with cis relation. That's why HA is giving doublet, and HA also giving doublet, HC also giving doublet. Again, this HA and HC, they are geminal couplings. You can see again they are going to split HA and HC. That we can call as like a geminal couplings. That's why A and C are chemically non-equivalent. As you can see here, it is very clear. So transcoupling, JAB, transcoupling, and similarly JAC, B and C, cis coupling, you can see here, very clear. The second one, HB, you can see. HA is transcoupling, and AC, that is like a geminal couplings, and HB, trans JAB, and below you can see cis. So always transcoupling is more than that of the cis coupling. Like cis is 6 to like 8, the coupling constants, but trans is 11 to 18. Transcoupling is more. So based on this coupling constants, easily you can distinguish cis and trans isomers. And HC also you can see cis coupling. So the distance between the peaks HA to HB, how much distance is there? Same HB to HA also same distance. That's why their coupling constants also same. If their coupling constants also same, means they are mutually coupling each other. The distance between the same protons who they are coupling, the distance is also same. That's why the coupling constants also same. If the coupling constants are same, that you can imagine they are neighborhood protons. They are coupling mutually each other. And similarly, if you see these cyclic structures, this is also a little bit more complex one. So this ABC, same doublet, doublet, and doublet, doublet. So this is like a diastereotopic protons, we can call it as a. This is very clear, ABC. And F, CH3. So there is no neighborhood protons. Obviously, it will give F singlet. But you can see here, E and D, they are geminal protons, E and D. Though they are attached to same carbon, due to this oxygen ring, epoxide ring, so there is no, it's like a CC bond rotation is restricted. CC bond rotation is restricted. So that's why these two protons, E and D, are behave differently. They are chemically non-equivalent sets of protons. So that's why it's like a geminal coupling. You can see in the spectra, D and E also coupling, leaning of any of the spectra, you can see here, it's like a doublet, doublet. So because they are mutually coupling each other, D and E. As you can see, D and E, they are doublet, doublet. This already explained previous spectra, doublet of doublet, doublet, and doublet. HA is coupling with HB, trans coupling, and then HA also coupling with cis. That's why HA will give doublet of doublet. 4 peaks you can see HA, and HB will give you trans coupling doublet, and then HC cis coupling doublet you can see. And you can see the distance, trans is more distance than the cis. And again, geminal couplings of DE, you can see very clear splitting. But geminal couplings are very less coupling constants because the separation between the they are with only 2 covalent bonds. But when it is vicinal couplings, so they are like separated with 3 covalent bonds. So these vicinal couplings can be calculated through the dihedral angle through Karplus equation. And the coupling constants. So what is coupling constant? The distance between the peaks is called coupling constants. So these coupling constants also field independent. These coupling constants also you can measure in edges. Their values are regardless of the operating frequency of the instrument. The distance between the lines is always same. The mutually coupled protons coupling constants are all same. For any two sets of protons, coupling constants are same because they are mutually coupling each other. These coupling constants are field independent, like external magnetic field and the instrument frequency. So there are different coupling constants. There are factors are influencing coupling constants like electronegativity and angle strain. So vicinal couplings, geminal couplings, and cis trans isomers. So cis trans isomers like 5 to 10, commonly around 6 to 8, and trans couplings 11 to 18. So these like homoallylic coupling, and even if you take aromatic compounds, ortho coupling, you will get 7 to 10 edges. Meta coupling 2 to 3. Para is very less because they are separated with 4 covalent bonds, 5 covalent bonds. So para is like a 0 to 1 edges, like a truly no coupling. So meta you can see 2 to 3, but ortho is more coupling because they are like a vicinal type. And even cyclic systems also you will get. So overall, if you see coupling constants, like generally geminal and vicinal coupling constants are classified as a short range couplings, and remaining are classified as a long range couplings. So if you compare with the chemical shift values and coupling constants in proton NMR, so 0 to 20, and even chemical shift values also 0 to 20 ppm, you can remember. So for example, if you take styrene, it's very clear splitting, you can see 17 hedges from A and B coupling, A to B coupling, trans coupling, it's like 17 hedges. Again B to C, A, again 17 coupling constant, because the distance between A to B same and B to A also same. That's why coupling constants are, they are mutually coupling each other because they are A and B are chemically non-equivalent. And HE and HC cis coupling, as you can see 11 hedges, is very clear AC coupling. And also BC geminal coupling, as you can see 1.4 hedges BC geminal coupling. So based on this, you can confirm that what type of coupling, based on this coupling constant, you will come to know whether it is cis coupling or trans coupling or vicinal coupling or geminal coupling, homoallylic coupling, ortho coupling, meta coupling, para coupling. So you have to remember these ranges of the coupling constants. For example, if you take butyric acid, it's very simple example. As you can see, carboxylic acid, anyhow, you will get singlet about 10 to 12, you will get it, the carboxylic proton singlet. But remaining CH2, CH2, CH3, how you can find whether they are in the chain? So if you, in the system, you see triplet, sextate, and then again triplet. If you see the system, like a triplet, sextate, and again triplet. If it is sextate is there, means easily you can recognize there is a neighborhood CH3, CH2 is present. And again you have to measure the coupling constant. You can see the distance between the peaks always same. This coupling constant 7.5, and here also you can say sextate also 7.5, 7.5, and also again triplet if you see 7.5. So the coupling constants are same, means they are like mutually coupling each other, means there is a CH2, CH2, CH3 system is present in the given molecule. So the coupling constant tells you not only these particular protons, you can study about the neighborhood protons. Next, chemically equivalent and chemically non-equivalent. If chemically equivalent protons will give you same chemical shift values, but the chemically equivalent may not be magnetically equivalent. That you have to keep in mind. So the chemically equivalent protons may not be magnetically equivalent. So if you see this example, very simple, CH2, CH2, X and Y substitution means the CH2, CH2 are chemically non-equivalent. So, but if you differentiate HA and HA dash are chemically equivalent, they are giving same chemical shift value. Similarly, HB and HB dash chemically equivalent, they will give same chemical shift value. And HA and HB, they are chemically non-equivalent, they will give different chemical shift value. But if you see HA and HA dash, HB and HB dash, so we will see the magnetic equivalency. So for the because of symmetry, this HA and HA dash have the same chemical shift values. Similarly for HB and HB dash, but now HA in this you can see staggered, the stable form conformational isomer you can write in this way. So then you can imagine one is back and one is, then you rotate, one you fix it carbon, another carbon you rotate like 80 degrees, 60 degrees, and then 180 degrees. So if you rotate this one, staggered is the more like a stable conformation. Now you can see, now HA will undergo spin-spin coupling to HB. HA will undergo spin-spin coupling with HB. But this will be different from coupling of HA dash to HB. So their electronic environment is indistinguishable. Electronic environment is indistinguishable. So they are giving maybe same chemical shift value, but they are magnetically different. We say that HA and HA dash are chemically equivalent, but they are magnetically non-equivalent. So if chemical equivalence means by virtue of symmetry within the molecule, their electronic environments are indistinguishable. They possess same chemical shift value. They are chemically equivalent. And magnetic equivalent means if each proton couples equally to a third neighboring proton, otherwise they are magnetically non-equivalent. So by seeing above example, A is like coupling with B is different from A dash is coupling with B. So they are chemically equivalent but magnetically HA and HA dash are magnetically non-equivalent. So simply chemical equivalence means chemical shift equivalency. Magnetic equivalence means coupling constant equivalency. This you have to keep in mind. Integration next. Okay, we have seen the chemical shift values, why they are giving different chemical shift values, so why the signal is splitting into multiple peaks due to spin-spin interaction. So they are splitting into multiple peaks. So and again we have seen the distance between the coupling peaks. So based on that you will come to know what are the neighborhood protons and their coupling constants like cis-trans isomers. And then integration. So the area of peak is proportional to the number of hydrogens in a spectrum. The integration measures the area of the peak, and the integral gives the relative ratio of the number of protons for each peak. So means how many protons are associated with that particular signal or peak you can measure. So means it will give the relative ratio of the protons but not the number of protons. So the integration give the relative ratio of the proton. For example, if you can see this one simple. So tertiary butyl methyl ether, tertiary butyl methyl ether. So here two chemically non-equivalent. These 9 protons are chemically equivalent and these 3 protons are chemically equivalent. So here two chemically non-equivalent protons are present. For example, if you see this methoxy 3.2 chemical shift values is giving singlet, and these 9 protons are giving again singlet because there are no neighborhood protons. It is giving singlet. But if you see the integration, if you measure, this is like a 2 spaces because it is equivalent to 3 protons. So 3 protons are associated with this methoxy signal. But here 9 protons are associated. The integration you can see measure, this is 3 times. 3 times is more, like a 6 spaces. This is 2 spaces, this is 6 spaces. So if you measure this integration, it's like equal to 9 protons. So this is equal to 3 protons. Similarly, this molecule, if you see, it's like a stepped curve, you can call it as a directly. It's like a steps. The integration is like a steps. This 0.5 equal to like a 1 proton D. This is OH, and another is 2 protons 1.5 proton 3 protons is 6. This 2 CH3 groups here. So based on that, so you will come to know through integration how many protons are associated with that particular signal. And this is also like ethyl benzene is like quartet, triplet, and aromatic. 5 protons, 2 protons, and 3 protons. And this isopropyl methyl ketone, as you can see, this BB is giving doublet, but C is giving septate 7. As you can see, 1, 2, 3, 4, 5, 6, 7. Is splitting is very clear splitting. Septate. So doublet and septate. In a molecule, if you have seen septate, directly you can write isopropyl group. That's it. It's confirmed septate. Then only you will get the septate. And then another one is like a singlet. A is singlet. And the integration also, it's 6 protons. is equal to this 3 protons equal. This septate C is equal to 1 proton. And this is also you can see is very clear. Triplet, this 2 CH2 CH2 triplet is giving because mutually coupling each other, triplet. And this olefinic protons are giving doublet. You see very clear doublet. And the CH3 6 protons are chemically equivalent, they are giving singlet. And topicity NMR, homotopic protons, anisotropic protons, diastereotopic protons. This homotopic protons means, for example, if you see this CH3, 3 protons are there. So if you replace one of the proton with X one time, so you will not get a chiral compound. So that's why, so these 3 protons are chemically equivalent. So means hydrogens are chemically equivalent or homotopic. If replacing each one in turn by the same group would lead to an identical compound. So means homotopic groups are an identical environment. For example, if you rotate 180 degrees, you will get same identical molecule. CC rotation, I am telling you. This where hydroxy group carbon and this CH3 carbon. If you rotate 180 degrees, you will get only identical. So these two molecules are identical. That's why it's like a homotopic protons. They are related to each other by bond rotation. And these homotopic protons are will give you same chemical shift value. It is very difficult to differentiate. And anisotropic protons means anisotropic groups are in mirror image environments, and they are related to each other by reflecting within the molecule, usually by a mirror plane. So, for example, if you replace CH3, CH2, Br, one of the proton, if you replace at one time with Q, so then you will get the two are, if you keep it mirror in between them, they are like enantiomers. So these enantiomers also cannot be distinguished through the NMR. They will give same chemical shift values. So for example, in this below examples, if you see two CH3 groups are there like cis 1,2 dimethyl cyclohexane. So there are mirror image environment. These two CH3 groups are mirror image environment. And again, one more example you can see the red hydrogens are homotopic because the CH3 groups are can be undergo rotation, and you can see they are blue hydrogens also like reflected each other. They are like anisotropic protons, but these red hydrogens are homotopic protons. Next, diastereotopic protons. Diastereotopic protons, they are obviously in different environment, so they are not related to any symmetry elements. So for example, if you see this example, so replacement of any one of the proton with Q, this proton are this at one time, so you will get diastereomers. Means these two protons are diastereotopic protons. And also below two examples are there. There is a blue hydrogen, red hydrogen. They are not interrelated to anything, and they are not symmetric related to any symmetry. So this red hydrogen, blue hydrogens are diastereotopic protons. And the next example also hydroxy compound. These red and blue hydrogens are diastereotopic protons because already you are having one chiral carbon in this molecule. If you replace at one time of any hydrogen, red or blue hydrogen, again one more chiral center you will get it. So that's why these two protons behave differently in NMR. So that we can call as a diastereotopic protons, like a cis-trans relation if you see in these molecules. And again vinylic protons, for example, mentally replace one of the HEA with Z, and also here also HB also you can replace with Z. So these two also we can call as a diastereomers, and these two protons we can HEA and HB also we can call it as a diastereotopic protons. So the diastereotopic protons will give you different chemical environment. For example, one spectra I will show you clearly. So we will discuss about the diastereotopic protons in NMR. For example, you can see in this molecule, the highlighted HEA and HB in the middle structure, HEA and HB are diastereotopic protons because already you have one chiral center here. One is phenyl, methyl, hydroxy, and this methyl alcohol. So there is this a chiral center. But the HEA, HB, they are geminal protons. But if you replace mentally one HEA at one time, this also become as a chiral center. So that's why these two protons are as a diastereotopic protons. When these two protons will are different chemical environment, so means they are chemically non-equivalent. That's why the HEA, HB are coupling, mutually coupling each other. They are giving doublet, as you can see very clear, doublet. So because they are diastereotopic protons. So the same explanation. They will give different chemical shift. Diastereotopic protons will give you different chemical shift value. And the height of the signal outside peaks are less intense than the inside peaks. This we can call as a leaning of the NMR spectra. So the leaning of the NMR spectra, how much leaning we have depends on how close to each other the signals are in the spectrum and how strongly they are coupling to each other. If they are closer they are, the greater the leaning and stronger the coupling. That we can call as a leaning. So HA and HB, you can see doublet, doublet. But when they are coupling constants and chemical shifts are very close, and they are, so then you will get only two peaks. So this is we can call as a. So as you can see, inside outside peaks are coming less into the less, and finally they disappear. So when this the chemical shift values are closer, same chemical shift value, the outside peaks disappears. In the same example, for example, OH peak. Sometimes OH peaks comes in the broad peak, sometimes sharp peak, sometimes you can see, sometimes you may not see, because it's depending upon the purity of your samples. If you are having any like a moisture or if any acid base in the solvent, so sometimes they may couple with the neighborhood, sometimes they may not couple. Sometimes they will give broad peak, sometimes they will give sharp peak, sometimes they may not appear. So based on deuterium exchange reaction, you can confirm whether it's OH or NH is present. And next one is the same example, aromatic system. If you see, it's like a mess. These are very clear. Singlet is very clear. OH broad peak is clear, and doublet of doublet is very clear. But if you see aromatic system, these 5 protons are like a mess up. So there are 5 protons are chemically non-equivalent. See He, this ortho protons are chemically equivalent, meta protons are chemically equivalent, and para. So 3 chemically non. So but here this should be doublet, triplet, and doublet should get. But it's like a mess because the chemical shift values of these protons are very close to each other. That's like it's like a mess. So it is not following the first Pascal triangular intensities, splitting intensities. So because when the chemical shift values are very close, so not only this ortho one is this proton is coupling with 1 2. It's like a true coupling. So when these chemical shift values are very close, so it will couple to third para. So that's why you will not get like a splitting pattern. You will not get very clear. Your coupling constants also is very difficult to. This we can call it like a virtual coupling. It's not like a true coupling. 1 2 coupling is true coupling, but 1 3 coupling is not a true coupling. So that's why we can call it as a virtual couplings. So many cases in aliphatic system, long chain one, like carboxylic acid, CH2, 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 like hexanoic acid. If you take hexanoic acid, last at CH2, CH3, their chemical shift values are very close. So that CH3 with CH2, it's supposed to get triplet, but it will not give triplet. It will give like a blurred triplet because the CH3 will couple not only the CH2, it will couple to the next CH2. So that we can call as a virtual coupling. So this enantiomers you can convert to like diastereomers, and again there is a method like using chiral derivatizing agents. These are like a chiral auxiliaries, methyl oxyacetic acid, biphenols, and O-methyl mandelic acid. These are like a chiral auxiliaries where you can convert enantiomers into diastereomers, and then you can take NMR. You will see the different peaks, how much diastemic ratio also you can. For example, if you can see take RS 1-phenyl butanol. This is like a racemic R and S enantiomers. But when it is coupled with like condensed with R most acid, so Mosher's acid, so like simple condensation like esterification, then you will get 2 diastereomeric esters like RR and SR. So then these one mixture, if you submit for NMR, then you will get the separation of the 2 different peaks. For example, you can see 7:3 ratio. So one is small intensity peaks, one is more intensity peak. So by using this one, you can easily separate these two ones, and you will get R and S. You can differentiate. So these enantiomers can be converted to. There are so many techniques like shift reagents and this one. And another one is there are 2 kind of spectra in NMR carbon-13. That is first order spectra, second order spectra. First order spectra, simple spectra. They will follow all the rules of like Pascal triangular, the intensity, splitting pattern, coupling constants. But secondary order spectra, it will not follow the first ones. It's like a complex spectra. The splitting pattern also not clear. So there are some of the techniques where complex like a second order spectra converted to simple spectra. So by increasing the first one is by increasing the like external magnetic field. If external magnetic field increases, the separation between the alpha and beta levels are increases. So then spin relaxation time is increases. When spin relaxation time increases, the spectral resolution also increases. That is one of the by increasing the instrument frequency. Like instead of 500 megahertz, you have to go for like a 900 megahertz. Then you will get more splitting pattern. And another one is spin decoupling or double irradiation, double resonance. We can call it as a. So simple, by removing of coupling between between protons by external method or technique is called decoupling. So we are using secondary radio frequency radiation, the secondary tunable radio frequency radiation. So to decouple the proton, so then instead of getting multiple peaks, you will get a single peak. So the multiple signals arises due to neighborhood protons coupling, like upward transition and downward transitions. So by using double irradiation technique, we can reduce the lifetime. Therefore, we will unable to resolve the spin interaction. To perform this one, we have to use secondary tunable radio frequency radiation. So we are using 2 times simultaneously radio frequency. That's why we can call as a double resonance or double irradiation. So for example, 2 chemical non-equivalents are doublet. So if one proton, if you decouple, then obviously you will get a singlet. And another one is contact shift reagents. So by using these contact shift reagents also, you can convert from doublet to triplet. Sorry, from complex spectra to simple spectra. So by you first one A, 6-chloroquinoline. So you can see the peaks are very close to each other. But when you added European complexes, shift bases, you can see much wider the signal intensities and the spectrum. So the paramagnetic European complexes with quinoline induce enormous downfield shifts. So in the signals of the quinoline. So these are the some of the European complexes: tis diphenylmethane, tis decafluoroheptane dione europium, and tis septafluorodimethyl europium. So in this, what happened? The shift reagent. So there is a single electron, unpaired electron. This unpaired electron spin in Europium 3 complexes. So they will transfer through the intervening bonds to the protons of the organic compounds. So that we can call as the contact shift reagents. So these paramagnetic unpaired electron, so is in the paramagnetic region. So when they are paramagnetic region, they will give more chemical shift. Then sensitivity of carbon-13. So that is proton. So same applicable for the carbon-13, same principle. And what are the factors influencing chemical shift values and even coupling constants and splitting pattern, Pascal triangle, everything is same. But here difference is the natural abundance of proton is 99.98%, but carbon-13 natural abundance is only 1.1%. For example, 100 molecules, 100 carbons in a molecule, if you see, only you can see one carbon-13 nucleus. So that you have to keep in mind. And if you see, more intensity of signal depends on 4 factors. That is natural abundancy, gyromagnetic ratio, and magnetic moment, and spin relaxation time. So here, when spin relaxation time is less, signal intensity is more. So this you have to keep it. But when compared to proton NMR, these all 4 factors are in favor to carbon-13 spectrum. It is very less sensitive, 6,000 times less sensitive than the proton NMR. For example, if you want to submit for proton NMR, 3 to 5 milligram sample is required. But if you want to submit carbon-13, you require 20 to 100 milligrams, because the gyromagnetic ratio when compared to proton and carbon is like a 4:1 ratio. So for example, precision frequency, if it is 100 for proton, for carbon-13 is only 25. So that is the reason you have to submit for more compound for this carbon-13, because gyromagnetic ratio is 4:1 ratio. And why need all factors are in favor to carbon-13, but why, how it is useful in the structural isolation of organic molecules. For example, if you take menthol, see, all in proton NMR 0 to 4 chemical shift values, all are coming like this, all 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 chemical and non-equivalent sets of protons are present. So, but the spectrum, intensity, so the magnetic moment of these protons are very weak. So, it is very difficult to distinguish the molecule. But with the same thing, if you see carbon-13 spectra, how many chemically non-equivalent sets of carbons are present? So, you can see 11 carbons are different carbons are there. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Sorry, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 chemical non-equivalent sets of carbons are there. As you can see, easily you can distinguish. So if you see in proton NMR, 4 ppm chemical value ranges, 320 hertz in this 80 megahertz spectrometer, and you use 1.9 Tesla of external magnetic field. If you see in the carbon 13, so 80 ppm chemical values are from 0 to 80 ppm. Here it is 0 to 4 ppm in proton NMR. But if you see carbon 13, 0 to 80 ppm. So in this, if you see same 80 ppm, 1600 like hertz, in this 20 megahertz spectrum at 1.9 Tesla, same. But so compared to proton NMR spectrum, carbon 13 NMR spectrum, 20 times more resolution. So in proton NMR, 100% splitting cannot take place, but in carbon 13, 100% splitting can take place. There are sharp peaks, more intensive peaks. In through carbon 13, easily you can distinguish how many chemically non-equivalent sets of carbons are present, and also you can distinguish how many protons are associated with that particular carbon. Easily you can recognize through the carbon 13, and also you can differentiate primary, secondary, tertiary carbons. Easily you can recognize through carbon 13, and also if purity of your sample also compared to proton NMR, carbon 13 NMR will give you very accurately, because as you can see, the compare these two spectra, which is more clear, which is more transparent, which splitting is how it is. So this is like completely decoupled spectra of carbon 13. Here also again, how many protons are associated with that particular carbon, easily you can recognize, identify by using spin multiplicity. For example, CH3 carbon will give you M plus 3, 1 plus 3. So means if 3 protons are associated, it will give quartet. 2 protons are there, CH2, it will give triplet. 1 proton is there, it will give doublet. So this you have to give. So for example, if we take butyric acid, as you can CH2, CH2, CH3, as you can see, very clear splitting. So triplet, triplet, and quartet. The CH3 is giving quartet, and next CH2 is triplet, next CH2 is like triplet. And the coupling constants also same as like proton NMR. But there, the same butyric acid coupling constants are 7.5 hertz. But if it is see the carbon 13 is 120 to 150 hertz. That you can see. Always the carbon 13 values are more compared to proton NMR. So this is broadband decoupling of heteronuclear. This is coupled decoupled one. So in decoupled one, so off resonance decoupled one, we can call it as. So there only you will get singlets, and the coupled one, homo broadband spin decoupling, you will get coupled protons. So coupled one, and as you can see, very clear, completely decoupled, off resonance decoupled. So by seeing the spectra, so total how many? 4 chemically non-equivalent carbons are there. So you can see simply 4 peaks are present. So easily you can recognize how many chemically non-equivalent sets of carbons are present. So proton decoupled, 2-butanol, and proton coupled. As you can see, proton coupled one. So very clear, doublet. This is CDCl3 solvent peak, and next one is doublet D, and then triplet, quartet, and quartet. This ACH3 and BCH3, quartet. This is carbon coupled one, proton coupled one. Above one is decoupled one. All are singlets. Very clear splitting. And this is like a 2-furyl pyrrole. So aldehyde proton, carbon 13, as you can see, 180 chemical values. And remaining here, 4 peaks are there, aromatic peaks in the region of these 4 carbons. And even see in the below proton coupled one. So this is like a proton and carbon 13 comparison. Next, DPT, depth, distortion enhancement by polarization transfer. So this will differentiate primary, secondary, and tertiary protons. One moment, please. Hello? Yeah. I'm in dark, so please call me later, okay? After 10 minutes. Right. So the depth or distortion enhancement by polarization transfer will differentiate primary, secondary, and tertiary ones. So you can see the depth of 8-menthol. This is CH3 protons, CH2 protons, CH, and all. So this is like a depth spectra. So what is the importance of this spectra? So easily you can differentiate primary, secondary, and tertiary protons. Always secondary protons CH2 are inverted to the spectra, remaining are with phase to the common spectra. So this is very important technique to differentiate primary and secondary, like CH3, CH2, and CH2. This is very clear. CH2, CH2, CH2 are coming down. In this molecule only we are having 3. 1, 2, 3. Having 3 CH2s are coming down to the spectra, inverted to the spectra, and remaining CH and CH3 are 1, 2, 3, 4, 5, 6, 7. As you can see, 1, so 2, 3, 4, 5, 6, 7. It's very clear. So based on this, you can easily differentiate. Wherever ambiguity is there, then you can perform this spectra by depth 135 degrees spectrum. So then you will get the differentiate the how many CH2s are present, how many CH are present, how many CH3 are present. Tertiary one, carbonyl, you cannot differentiate. Applications NMR in post-genomic era. Not only that, so the biomolecules like high molecular weight compounds like proteins, like not only proteins, even DNA RNA interactions, drug design and gene silencing. So how drug protein interactions are taking place, those also you can study by using 900 megahertz instrument. So strong peptides like big peptides like proteins, everything you can estimate through the proton NMR. So for example, if you see this 800 megahertz, 7.6 kilodaltons molecular weight of this protein, one-dimensional spectra. So at 30 degrees centigrade they have performed. So you can see the region NH and aromatic regions in this, and aromatic regions and aliphatic regions. So MRI, it's a magnetic resonance imaging, is non-invasive. So because you are using radio frequency radiation, this radio frequency radiation frequency is very less when compared to like UV and IR and X-rays. So even X-rays are like invasive, but this MRI, like radio frequency radiation, is non-invasive. So it is not hazardous. And nuclear is omitted because of public fear that it would be like a radioactive. That's why they changed nuclear magnetic resonance to magnetic resonance image. They omitted the nuclear word because of fear. So only protons in one plane can be in resonance at one time, and the computer puts together slices to get the three-dimensional structure of the like a molecules. And tumors, by using this tumors readily can be detected. So this is like how this NMR is useful for the common man, where we are going for like diagnostics of any abnormalities there in our body. So easily you can distinguish that even minute problems also. By so how this like NMR is useful for the common man, not only for structural elucidation. So it is like playing a pivotal role like in medicine. And for example, homogeneous field, inhomogeneous field. For example, if there is no abnormality, even brain or whatever, wherever it is, you can see the pressure frequency is same because our body is made up of with proteins. Proteins are like because of peptides. Peptides are because of amino acids. Amino acids also like protons, carbons, like a sulfur or oxygen. So which are magnetically active, they have their own precision frequency. So if there is no abnormalities, that means they have like precision frequency same, they are moving same, and you will get only one signal. This is like a homogeneous field. So then if it is inhomogeneous field, if any abnormality is there, obviously their precision frequencies are different. When their precision frequencies are different, you will get different signals. As you can see, inhomogeneous field. So there are three different precision frequencies. So there you are getting different signals. So this will give you so principle of like a spatial resolution through the field gradients. So in three-dimensionally they will take it. So you will get the peak intensities based on the peak intensity, small intensity, one dot, two dots are there, the intensity is more. So like three-dimensionally they will take it. So they will see exactly where that problem or tumor is there. So easily can be detected by using this MRI image. So this 3D image always you will take XYZ axis like a three-dimensional structure. So based on this, this MRI image guided for the surgery. So this is like accurately where they have like operate the surgery. So this will give like a clear information. MRI will give you clear information where exactly it is located. So there they will operate the surgery. And MRI and localized MR spectroscopy. So based on the signal, they will identify and regions of the brain and mapping functions of brain using NMR image, that fMRI we can call it as, because our brain is the most active part of the body. Different regions of the brain perform different functions, and speech, memory, sensation, liking, disliking, violence, agitation, taste, smell, emotion. And while performing these functions, what happened? The blood oxygen supply to this particular regions will vary. Such variations also in the brain mapping, you can see that oxygen levels also you can study. Nuclear magnetism in teenagers, the rate of precision of communication, comprehension, reaction are different in the teenagers. They are highly selective, but different active regions of the brain based on their IQ. Those things also you can identify. And link between watching violent videos, games, and aggressive attitude in teenagers, especially children. When they are alone, they are watching uh, uh, like violent videos. So sometimes they behave differently. So if you undergone for MRI, exactly what is the problem, so easily you can recognize. So these are the some of the applications we need to mention. So thank you. I think I have taken 1 hour 20 minutes, 1 hour 25 minutes. Thank you. Now open for discussions.
Sir, thank you so much, sir. Uh,
Hello.
Hi, sir. Are you audible, sir? Am
Yeah,
I
audible,
audible?
audible.
Yes, sir.
Yeah.
Thank you so much, sir. Believe it or not, I am still struggling to find the right words to properly describe how fantastic your presentation was, sir. Thank you so much for
Thank you.
delivering us such a remarkably outstanding presentation, sir. So, from audience side, we had two questions, sir. One is from Dr. Subharjit Mantri. It was
Mhm.
posted in his question is it possible to record 13C NMR for stable microemulsion in liquid state?
Yeah.
He posted a question
Yeah.
like that, sir.
So I'm not
And
clear about this emulsions because it's like a formulation. Micro emulsions in liquid state means it's like a formulation one. So liquid state means yeah, if it is stable, we can do it.
yeah, sir. Okay,
Yeah.
sir. Thank you, sir. There is one more question, sir. You just check it out, sir. Which method is most useful, whether PMR or NMR for structural elucidation? I think there
Both
is
are
no.
important. Both are important. Both are important
Okay.
because in proton NMR you can see how many chemical non-equivalent sets of protons are present. In carbon 13, how many chemical non-equivalent. So both are useful for the structural elucidation.
Okay, sir. Fine. Thank you so much, sir, for giving us your valuable time to present your presentation in our platform. Thank you so much, sir.
Yeah.
And just now, I request Swarnalata madam to take over that.
Sir, sir, now I welcome uh, and introduce the next speaker, Dr. R.M. Prakasham, sir, Chief Scientist, Department of Medicinal Chemistry and Biotechnology Department, CSIR, Indian Institute of Chemical Technology, Hyderabad. He received post-graduation degree from Gulbarga University in 1984 and PhD from Northeastern Hill University from in 1990 and postdoc from Center for Cellular and Molecular Biology, Hyderabad in 1991. He received honors and rewards of Talented Industrial Award 2014, International Gold Star Award 2010, DBT Overseas Associateship Award 2008, CSIR UGC NET Fellowship Award and IICT Best Performance Award for the year 2001 to 2. His credit, he published 160 research papers in national and international journals, including 27 patents, chapter in books, and invited lectures to his credit. Thank you, sir. Hand over to Prakasham, sir.
Yeah, am I audible? Hello? Am I audible?
You are
Yeah,
audible,
sir,
sir.
you can continue the section, sir. You can continue.
Okay. Share. I am just taking out my this one. Share this one application window, isn't it?
Yes, sir, of course, of course.
Hello.
Yeah, sir, of course, sir. Click on the
Application window.
shade. Yeah, click on the shade screen and then application window, PPT, and you can check it out, sir.
PPT. I have to open it, isn't it?
Yeah, yeah, sir. Okay.
Is the PPT is visible to you?
Yes, sir, just a minute, sir. Not it, sir, not it.
I have shared it.
Yeah.
Is it okay?
No, so still it was not been visible. Sir, you click on the share screen, application window, then
One
select
minute.
your PPT file and then share.
1 minute. 1 minute. Yes, application window.
Yeah.
Share button is not active.
Okay, sir.
Is it visible? Full screen is visible?
Yeah. Yeah, sir, of course.
Okay. Now can I start it, that one? Am I audible now?
Yeah, sir, you are audible, sir. You can
Hello?
start the section. Yeah, sir, you can. You was audible, sir. You can start the section.
Good afternoon, I can say. It's 1 minute past 12 o'clock. And after seeing a nice talk and excellent talk by Dr. N. Shankaraya, who is head of the department, I am happy to see that he is from IICT fraternity, IICT club. And I also see the Mahathi College of Pharmacy, a spectrum of people, and especially the three persons, Amarnath Reddy and Senthil Kumar and Lakshmi Narsaya Garu. And along with that, I would like to thank Dr. G. Swarnalatha, who was the contact person for the entire thing. And today, the talk of the webinar or title of the webinar is very interesting to see that novel insight in antimicrobials and analytical techniques. Whether you look at the antimicrobials or antibacterials or whatever it may be, antimicrobials are known since Alexander Fleming onwards. However, the things are changing from time to time with the new antimicrobials coming into the picture, and there is a lot of modifications. First generation, second generation, third generation, fourth generation, or so on. And this is a very interesting to know that one. In the last 30 years, there is no new antibiotic is discovered so far, and there is a lot of demand for antimicrobials as the resistance is increasing for the several microbes for the existing antimicrobials. So in this context, I would like to see the today as the emerging trends in antibiotics as I am looking. I am Dr. R.S. Prakasham as a Chief Scientist in Medicinal Chemistry and Pharmacy, Indian Institute of Chemical Technology. And if you look at that, though everybody knows that what is an antibiotic, exactly the antibiotics are the two types, basically two types. Though they affect any antibiotic will affect the life of the microbial. However, they can be a microbicidal or microbicidal, or both are different in this. And in the term antibiotic is accepted for the broader definition. This can be used for the bacteria, virus, fungal, parasite infections, but viral is a very difficult to know as of, unless they are in a particular bacteria, and then only it can be there. That means if the bacteria is infected by viral, killing that bacteria, you may stop the growth of the viral. That is the way we are talking about the antibacterial, antimicrobial versus towards a viral case. So there is a level of importance also is a most important. In this is that current treatment in human and patients are human patients and animals, 68% of the acute respiratory tract visits are prescribed by the antibiotics. Of these, 80% prescriptions were unnecessary according to the CDC guidelines. This is a most important issue. Because of this only, the resistance is increasing day by day. Unnecessary prescribing the things. Unless we know that one, it is essential to do it. It is necessary to prescribe it. As I said, is that there is two types of the antimicrobials. One is a bacteriostatic agent. Another is a bactericidal agent. What is the static and cidal? Static is nothing but just to stop the growth. However, it will kill, it did not kill the, it will not kill the microorganism. This is called static, maintaining the same status, just like a judiciary system, you maintain the status quo maintenance. If you look at the bactericidal agents, they kill them. And there are so many things. It's a bacteriostatic, several antibiotics are there. Bactericidal, several antibiotics are there. If you add a particular drug in a particular system, then if the cells are going to die within a 10 to the power of 3 cells, growing cells, then we can say it is a bactericidal. If continuously grow, but it is a system is not developing much of this one, this is a bacteriostatic. And if you look at the what is the importance of the microbes in a human being, our human being is a very much associated with the microbial system. If you look at the mouth, at any given time you have a 10 to the power of 7 to 10 to the power of 8 number of microbial cells are associated with your mouth. If you look at the stomach, 0 to 10 to the power of 3. If you look at the small intestine, again there is a lot of variation with duodenum and jejunium and ileum. If you look at 10 to the power of 3 to 10 to the power of 7, there's slight variation of the system. And large intestine, you can see the highest number of the microbial population available at any given time, 10 to the power of 10 to 10 to the power of 12. Even your stool having a same amount of the microbial system. So the entire life is associated with the microbial association of the human being. If you look at the another thing, even if there is so many different number of cells are available, it is not a single type of microbial cell. There is a several variety of the microbial cells are available, just like lactobacillus, streptococci, enterobacteria, enterococcus, faecalis, bacteroidetes, and bifidobacteria, peptococcus, peptostereococcus, ruminococcus, clostridia, and lactobacilli, etc. All these things, if you look at the system, they are the beneficial microorganisms. We are talking only beneficial organisms which are associated with our life. If you look at the what will happen if the microbes are not associated with your body? If the bacterial flora, whatever I said in the previous slides, if they are getting imbalance, that is a 10 to the power of 7 or 10 to the power of 12, whatever the system is imbalanced, any variation in the microbial flora, either more or less, then there will be a lot of problems associated with it, lot of discomforts. It may be constipation, diarrhea, fatigue, pimples, dark speckles, and cardiovascular diseases, reduced immunity, vaginalis, and aging of cells also associated with this one. Irritable bowel syndrome, Alzheimer's disease, chronic hepatitis, liver cirrhosis, and colorectal cancer also is associated. That's why the maintenance of the a proper microbial flora is essential. These beneficial microbial flora also called as a probiotics. And these are the internal systems. Even if you look at the external also, bacterial microbial flora also associated with a dark and dull complexion and spectacles, ains, and bad breath and dry mouth. Even you have a red pimples on the chest or on the back, coarse and dry dull skin also associated with a microbial flora. And many chronic diseases caused by the caused is because of the reabsorption of the toxins, and lower abdominal bulge also is possible with the microbial flora. Hemorrhoid, smelly fats, weakness, swelling, and discomfort of the lower limb also sometimes is associated with the microbial flora. Hence, one should have a proper microbial flora is essential. And if you look at the bacterial infections, if you look, these are the beneficial. If these beneficial microbial flora are contaminated or it is introduced by the any other disease causing microbial infections, then you will have a lot of problem. Especially if the bacterial meningitis is associated with the streptococcus pneumonia, and these are the different microbial flora. Otis media, it is streptococcus pneumonia, and pneumonia is then again there is a 3-4 types: community acquired, atypical, and tuberculosis. All these are different microbial flora. Even if you look at skin infections, also is a streptococcus aureus, streptococcus pyogenes, and pseudomonas aeruginosa. And you can have eye infections, sinusitis, upper respiratory tract diseases, gastritis, and food poisoning, urinary tract infections, and even you have a sexually transmitted diseases also associated with the microbial flora, which is of the disease causing and which are associated when not associated with a human being. And all these microbial flora has to be killed or used to be stopped for growth and their subsequent effects, to reduce the subsequent effects. Antibacteria discovered in Alexander Fleming in 1928. This is as a wound at that time for the entire world for killing the microbial diseases or microbial population which is causing them. And the second thing is that the all antibiotics does not have any specificity towards the whether it is a good bacteria or bad bacteria. Hence, one has to be looked at the proper replenishment of the good bacteria while taking the antibacteria. And antibacterial activity, as I told you, bactericidal and bacteriostatic. If you look at the bactericidal, if it kills the organism, example is the beta-lactam and vancomycin and fluoroquinones, aminoglycosides, daptomycin, metanzole. These are the bactericidal. That means they kill completely the bacteria. Whereas if the bacteriostatic is there, this inhibit the growth. Especially bactericidal one basically act at the either at the cell wall level or at the protein level, completely stop it. And this macrolides and other things as a bacteriostatic relapses the can relapses the discontinuation. And what is happening is that whenever you give it this one, they stop for a certain time. And if you remove that antibiotic from the site, it again able to revive the growth. And whereas the other things cannot be revived in the bactericidal cases. And there is a several market potential for the microbial market value of the antibacterials. Though 2018 it was 3.63 billion market, and which is expected to be 5.23 billion market by 2024. Within a span of 6 years, it is going to almost double. And there is a certain bactericidal static antibiotics are given as an example. And the classes of antibiotics, there are several classes of antibiotics are put into the system. Beta lactams, polypeptide, aminoglycoside, tetracyclines, ampinocols, and lipopeptide, and macrolides, and you have oxolidinozones and glycopeptides, anamycins, quinolones, and lincosamides, etc. Each class of the microorganism has a particular site of action. All will not work in a particular, all will not work in all the things. For example, if you look at cell wall inhibitors, there is a beta-lactam antibiotics are taken in. All beta-lactam antibiotics are working only with the cell wall, on the cell wall, which is inhibit the cell wall formation, peptidoglycan layer formation, and then go. In that also, you can see the penicillins were the first class of antibiotics, which these penicillins have given the semi-synthetic penicillins, several semi-synthetic penicillins. When the penicillin is a natural source of antibiotic, which is acquired by the resistance acquired by the microorganisms, these penicillins have been modified by changing the structure by addition of the certain other groups at a particular position. Then they become a semi-synthetic, partly synthesized by the bioorganism, followed by the chemical synthesis, chemical modification. You can say ampicillin, amoxicillin, penicillin, again benzothine, and you have a carboxylin, and you have a dichloroanicillin. Such things also nowadays are getting a resistant. For this also, the bacteria is getting resistance. The second class of the beta-lactam antibiotics are cephalosporins, where the penicillins, cephalosporins had an advantage over penicillins, but cephalosporins also is getting resistant by the microorganisms. So there is a first generation, second generation, third generation penicillins, the cephalosporins also came, and they are each one is a specific. Those site of action is same, but only thing is that because of the structural variation, they could not able to fit into the particular system or a cell wall wherever it has to work it. Then they are working for killing the microorganisms. But microbe also very smart enough to change such system. Then they are becoming a more resistant. And carbophenums and monobactums are nowadays they are coming a very important for this one. But even this also, all these also affect the microorganisms are getting resistant. Then this is because of this certain enzyme produced by the microorganism, which is breaking the beta-lactam ring of the cephalosporins or penicillins or carbophenums or monobactams. Hence, there is a beta-lactamase is another enzyme came into the inhibitors, and then other bacteriostaticin, vancomycin, all this clavulanic acid and other things. That's why nowadays all ampicillin tablets or amoxicillin tablets or cell wall mediated things are given along with the clavulanic acid. Clavulanic acid will inhibit the beta lactamase, and then that's why it will work for the microbes. As there is a again there is a what we can call as a stoppage of the inhibitory action, resistant action by the microorganisms. And if you see that one, there is a other slide I was telling about the different types of the antibiotics, which will be site specific. For example, cell wall synthesis related antibiotics are this one: cycloserine, vancomycin, bacteriocin, penicillin, cephalosporins, monobactams, carbapenems. All these work in the cell wall. Whereas if you take a DNA gyrase, nalidixic acid, ciprofloxacin, novobacin, or quinolones will work on the only DNA gyrase. RNA elongation, they work actinomycin. And DNA director RNA polymerase, rifamycin, streptoviricins, and protein synthesis, 15S inhibitors, and erythromycin, chloramphenicol, and 30S inhibition is a tetracycline, streptomycin, gentamicin, kanamycin, or a variety of things. And like that, there is a separate each group of organ. And if anybody asks this, there is a ribosomes also present in human beings, but there is a difference between the bacterial ribosome or prokaryotic ribosome versus eukaryotic ribosomes, where eukaryotic ribosomes are 60-40, whereas bacterial or prokaryotic is 50-30. Hence, these specifically synthesize or specifically affect the 30S or 50S ribosomes. Hence, they will not affect anything. Even a protein synthesis also, there is a certain variation in the prokaryotic versus eukaryotic. Hence, we have a different. Hence, they will not work on the human being. And if you look at the spectrum of antimicrobial compounds, there is, you can see there is a penicillin was a green at the time, and by the time cephalosporins came, that it became very dangerous, and carbapenems also is a very dangerous. Initially they are green and slowly resistant develop. As the resistant developed, then there is each antibiotic is been modified and bring into the new system. So you can see the quinolones and maxofilin and metrogendol now is a at least somewhere that whatever the green or a blue type are there, nowadays they are working effectively for the particular time being. If these also getting a red color, then we will have a problem in a future for the system. And antibiotics are not only used for the microbial infections, they are also can be used during the transplantation to restrict the infection. Even a dialysis also, during the dialysis also they use. Again, there is a restriction of the infection. Suppressive immune system also, it is all used. Giant replacements also used. All under these conditions, there should not be any opportunistic microbial system should not enter into the system. That's why they are using as a precautionary measurement purposes. So now there is a buzzword is coming into the worldwide that is called AMR, antimicrobial resistant system. AMR are resistant to resistance of a microorganisms to a particular antibiotic that was originally effective in treating the infections caused by it. So this is called AMR. Why India needs a crab antibiotic overuse? Because there is a India's bacterial disease burden is highest in the world. Is because you can look at the any country, if you go to the system, especially developed countries, no medical prescription or a practitioner will give a without prescription any antibiotic to you. But in India, you can get, anybody can get it. This is, and moreover, there is a unqualified doctors present in the Indian system also prescribing left and right for the antibiotic, even without knowing the whether this will work or not. And large population suffers from the disease like diabetes, hard elements and cancer, making them prone to infections. Because COVID is this one way, especially we can hear in the COVID-19 situations, and such systems also associated with this. And 40% children are malnutrition at the risk of the infections. If your immune system and nutritional system is properly working, there is a choice not to use the antibiotics. But because of the malnutrition systems, then antibiotic usage also you are becoming sick, and then you are using the antibiotics for treating the system. More and more drug resistant bacteria are being identified in India. And what is the reasons for increasing the antimicrobial resistance in over the either use? 1 minute, I am getting my battery. Swati, yes, Swati, battery. Chill in that. 1 minute. So there are several possible reasons also associated with the antimicrobial resistance in this one. One is the increased antimicrobial consumption, as I said about the previous slide, and irrational use of the antimicrobials in clinical therapy and agriculture. Agriculture also they are using, and especially the fish culture, what we call a sericulture, fish culture, and other things also they are using it. And that is animals also they are using, and which are more dangerous than human beings, because there is no restriction or no surveillance in use of the antibiotics in animals. And more susceptible population for resistant microorganisms are increasing, and dissemination of ARGs due to the increased antimicrobials also is becoming it. And antibiotic resistant facts, if you look at that one, what is the, still now we know that each antibiotic can work at particular things, and use of antibiotic can be can kill the microorganisms. But what is the microorganism is taking its own care by surviving against the antibiotics. Just like our thing is survivable of the fittest, microorganisms also looking for the survival of the fittest. Hence, they are developing several strategies to looking at the to reduce the antimicrobial effect on them. Especially if you are looking at the DNA synthesis gene overexpression by to reduce the DNA synthesis related things. Whatever the red color one is the mechanisms they develop, the microorganisms are developed. Especially whenever they are protein synthesis, cell proliferation is taking the enzyme deactivation systems are developed. Or they are pumping out the whatever the antibiotics you have inserted by using the drug efflux genes. And enhanced DNA repair they are taking into the consideration, so that the whatever the DNA is affected during the process or in presence of the antibiotics, that is eliminated, and the original DNA they are taking. And they are also resisting the drug-induced cell cycle arrest and apoptosis, even in certain cases. So with this, what is happening in the present system, acquired resistance is also is occurring. Acquired resistance means it can transfer the anti-resistant property from one microorganism to other microorganism in certain cases. And because of the, suppose if the one's microbe is resistant to the ampicillins, and another is resistant to the protein synthesis antimicrobials, they interchange the system or antimicrobial protection system, and they become the resistance for the both cell wall synthesis and protein synthesis, and vice versa in a different things. Similarly, in that case, mostly Staphylococcus aureus, now it becomes a very dangerous because a multi-resistance, this sensitivity is resistant system as well. Vancomycin resistance also is the MDR, XDR also is a gram-negative respiratory pathogens also becoming a more resistant, more and more resistant for the several antibiotics, not one antibiotic. And they are less toxic to antivirals and anti-cancer agents. All antibiotics are less toxic to antiviral or anti-cancer. Anti-cancer is associated with the human cells, hence human cells will not affected by the antibiotics, hence they are called resistance. If you look at the system is a worldwide, antibiotics resistance is becoming bigger and bigger day by day. And you can see in the 23,000 deaths in the US caused by the antibiotic resistance infections every year. And 2 million illnesses in the US caused by the antibiotic resistant infections every year. That means because of the resistance property, they are becoming 2 million people are becoming a more affected by the other bacteria. And even if you look at this one, diabetic people are 1 million people are affected because of the AMR system, cholera, cancer, and 2050 you expect the 10 million tetanus. Road traffic accidents also is associated with antibiotic, because whenever you have an injury, again there is a microbial invasion, and that microbial invasion may cause the infection, which if the microbe is antibiotic resistance, you have a problem with that. And you have a measles also, diarrhea cases also, something like that. There are several, and India is under superbug threat because of the unrestricted use, and there is no surveillance and everything. And out of every 10 patients with the infections of SU, 4 have a drug resistance bacteria, even in ICU conditions where you are expected to have a more effective system. So the danger is very high. Antibiotic misuse as a spread of the natural process of resistance, rendering some antibiotics useless. Experts warn we are at the dawn of the post-antibiotic era. So we should be very prepared for the catastrophic threat against the, just like a terrorist war. And if you look at the CDC has given a very good clear picture, and with the Clostridium difficile, you have every year 250,000 people are affected and 14,000 people are dead. And US is almost all spending to control this disease. You can see that 10 to the power of $9 million. $9, 10 to the power of $9. If you look at the multi-drug resistant Pseudomonas aeruginosa, every year they are expected to, the deaths are approximately having a 440, and people are affected is 6,700, and $50,000 billion dollars are every year spending. Salmonella also, you can see the 1 lakh people and 1,20,000 people, and Actinobacter, and even if a carbapenem resistant Enterobacter also, and even methicillin resistant Staphylococcus aureus also you are affected by the serpent. So this is CDC's information is very alarming for the not only US itself, where clean and everything is more we can say of the most effective, clean and hygienic place. And you can look at if such situation is happening in US, what will be the situation in India and some other third world countries where poverty is more. And there is a if you look at the journey of the antibiotics, the first antibiotic introduced, when it is introduced and when it is becoming a resistance has developed. Even if you look at a penicillin is approximately 1928 is taken, and more effective use is 1943, but first penicillin resistant is identified in 1940. And the tetracycline is introduced in 1950 and erythromycin in 1953. And by the time 1959, approximately 9 years, within 9 years, you have got the tetracycline resistant or Shigella. And erythromycin also is, you can say, 53, 68, and methicillin also for 60, within 2 years it came, and penicillin pneumococcus is 1965. Like that, if you look at one organism, particular organism as developing its own resistance factor against a particular antibiotic, within introduction, of course, recognition is the identification is the most important when it is happening. The gentamicin is introduced in 1967 and resistance is observed in 1979, and vancomycin 72, and you can see 88. And like that, ceftazidime and already in 85 within 2 years. Like that, levofloxacin, linezolid, and daptomycin in 70. All these things are getting very affected within a overall. If you look at the system, when an antibiotic introduced, approximately 30 years is becoming, and 30 years is taking to become a resistant. Most of the microbes are getting resistant against the particular antibiotic. So 30 years span is given. So what is the, I said, community transfer, or we can take up the how does antibiotic. So if the bacteria is high number of bacteria, few of them are resistant, and then slowly they transfer their resistant factor into a particular thing, first initially into the group and then genetically transfer, so that they will be getting affected by slow one by one. And if the improve antibiotic use, what we can call about the 70% prescripts are likely necessary and 30% are unnecessary, which is the study according to the CDC. And agribusiness also is agriculture and human health also associated with the antibiotics. And some people are using the milk overproduction or poultry or pig, these antibiotics over the taking the meals or whatever it may be transferred to the human being, and then novel genes, and you can look at the natural biomolecules are developed, but even though there will be a lot of problem in associated. And novel gene discovery is also associated by the antibiotic resistance. And one can look at the metagenomic DNA isolation under domain searcher. Based on that, one can look at the what is the changes occurring with the antibiotic introduction into the microbial system. And what is the novel approaches for the potential microbials? One has to look at the, as you know, that resistance is a more and more dangerous. One has to look for the new antibiotics. That's why nowadays people say that all mesophilic microorganisms have been 90% or 70% is looked, but marine microorganisms are not looked for the novel antibiotics. So now the most of the recent trend is going towards the marine actinomycetes strains isolation and doing it. In addition to that, there is a unexplored niches are there. This is a marine antibiotic is an unexplored niche, one of this. And uncultivable microorganisms. Generally, there are two types of the microorganisms are exist in the world. One is a cultivable, that means you can grow in the laboratory. Another type is the uncultivable. Uncultivable means they need a special attention, very extra special attention to cultivate the microorganism. Those are the rich source for antimicrobials. The simple example I will give is a cell culturing system. The people still add the serum as a one of the component in the tissue culture things. And if you know the serum components particularly, you can synthetically prepare it. But since we don't know the serum related components, hence we are adding the serums. Similarly, here uncultivable microorganisms also does the same thing. We have to look at special care in how to use, how to add. I'll go through in a subsequent slides. And genome mining also may help in the system. Genome mining in changing the genome size or genome structure. One can look at the, suppose if the epithelon B is there, epithelon B is a anti-cancer drug. I'm talking about the not antimicrobial, but this is a gene. They do it a hybrid gene preparation to synthesize the more and more epithelon. Similarly, one can look at the resistance factor wherever it is coming. Why don't we change the genomic structure and develop the novel particular antibiotic, which is supposed to be new for the microbe and to kill the microbe. And metabolomics also another pathway of looking at in synthetic biology, another one, smart screens and chemical and genetic network also. Basically, if you look at the antimicrobials totally, lot of peptone and protein antimicrobials are more compared to the other antimicrobials. If you look at the peptone related antimicrobials, one can take the lot of opportunity in changing their structure, engineered antibiotics, all D-aminopeptides, because all aminopeptides can be used, but D-aminopeptides have a special unnatural amino acid peptides, where we have a 20 natural amino acids, but you can use unnatural aminopeptides. They can modify the protein and antimicrobials, because all living organisms use only natural amino acids. If you use unnatural amino acid related systems, then they can interfere with the microbial system. And then beta amino acid peptides, modern glycoconjugates, and multi-specific antibiotics, monoclonal antibiotics, cytophore conjugates, and analogs. Like that, you can use the antibiotic enhancers also. You can use it and change the system. And other antimicrobials, you can look at the photo-switchable antibiotics and specific species-specific library compounds. All these things I will take into the subsequent slides. What is the one of the major novel antimicrobial development is the component engineering process. You can look at the first predict the system, demonstrate it, and develop the regulation aspects of the either by media optimization, co-culture, with the help of the phylogenetics, and bioinformatics, transcriptomics, and proteomics, and metabolomics. And using these, you regulate the DNA transcription or proteins or natural products, biosynthesis, or gene cluster, and producing the organisms. This in turn gives the engineered activation, which again helps in the metagenomic sequencing inputs. With the inputs of this one, heterologous expression and engineered synthetic biology, one can develop using the bioengineering aspects entirely different natural product analogs, which will help in the system. So what is the components you are associated with? If you look at the x-axis, error-prone PCR is essential. And you have an insertion and deletion of the several amino acids, circular permutations, multiple stimulations and sequential substitutions, insertion and deletion of the loops, and homologous recombination and domain swapping is one of the. All these things look at the directed evolution of the particular system. and with amino acid sequence. If you take a homology model with along with this one, then you can develop active site targeted substitutions or amino acid contributions. And even if you look, the more and more information is coming about the mechanism and kinetics and 3D structure, bound translation state and lags, and mode of transmission states, either QM or MM, including dynamics, rational design, altered substrate specificity, and rational design of the new reactions will come into the picture, which will give the new components. One of the example for this one is the new antibiotics. The molecular genetic and structural biology use that one and modified microorganisms. You get it? New antibiotics, engineered understanding of the metabolism. For a simple example is that mupirocin, an antibiotic, and which is can be modified using the pseudomonas, pseudo-altromonas, and by the changing the structure at the red locations. And this is a new antibiotic, and this new bioactive agent using a engineered biosynthetic pathway of pseudomonas, and then it is worked very well in the system. Antibiotic enhancers is the another one where two antibiotics are linked together or put together and then developing a new antibiotic. If suppose if the transpeptidase is there, you can stabilize it OSL enzyme, then you can get it in the chart. Like that, serine beta lactamases by changing the enzyme structure somewhere in the structure, and benzoyl penicillin bound to the PPB also can be. So these, what will happen, use of these linkers and everything, the membrane disruption will take place. They enter inside and they protect the again this one. And this is the, there is another linked based systems, is a ferric siderophore linked with a drug. You can get it a new antibiotic. If the ampicillin is linked with some linker, enterobacterium, new siderophore is formed. This siderophore enters into the system and then affect the respiratory position of. Like that, you have an antibiotic linked in ferric also. There is another thing. And engineered phases also, you can take it phases, viral phases, just like viral phase, indigenous phases. And you can look at the different genetically modified bacterial phases. You can call it as a, they can have an industrial application, detection applications, therapeutic applications, biocontrol applications, veterinary applications. What it does, reducing the bacterial load by lytic phase or engineered phases, where you will not be using a core protein, genes will not be there, only DNA related, some other things will be there. Administration wise, they are very effective orally, typically or systematically, and they can use a free phases or phase infected bacteria, very much experimental. They are doing it something now. Usage during the first step infection, catch infection on the time before harden the infection, and use those phases for the modification of the antibiotic. So that way, the phase combination, antibiotic dose and timing with phase administration changes, optimal duration of the antibiotic and phase therapy changes, potential and de-escalate phase and antibiotic therapies also changes. Like that, you can have a host related effectiveness and target pathogens also is important. And engineered phases activity profile, if you look at phage engineering, can be done by the non-lytic toxicity, enhanced longevity, altering the immunogenicity, minimizing the patient toxicity, host range expectation, host range switching, targeted plasmid degradation, genome specific toxicity, like that. Even in this also, there is a biological systems, chemical system, physical systems also associated in each and every case. If you look at the hydrophobic interaction, something like hydrogen bonding elements, crystalline regions, or complementary oligonucleosides, everything is possible in a particular system, either using the UV reaction or cross-linked molecules or biologically changed peptides or everything. And with these tissue engineering scaffolds can be prepared. This scaffold will help effectively site transportation. Suppose a hydrogel is taken, hydrogel is classed into the polymer, and they can be delivered at a particular site. You can look at some other liposomes and other things just like that. You can look at. And methods to evaluate antimicrobials, there is a lot of systems. One has to know that whether it is antimicrobials are effective or not, whatever we are using. And evaluation of the antimicrobial surface designs that release of antimicrobials is a one way, or contact killing another way, or non-adhesives looking at the other way. So for each evaluation, you require a careful selection and evaluation methods. One is basically the common used one is a agar zone of inhibition method. And another is a suspension method, where we can talk about the MIC, MBC, or IC50 values. Methods of compromising a high area to volume ratio, another one. Addition based methods also there, biofilm based method also there. And this addition based and biofilm based methods are nowadays becoming more and more. And even in ICT, we are working on biofilm based methods and addition based methods for the evaluating the antimicrobials of the particularly synthesized one. There is a photo switchable antibiotics are there, where photo switchable can be, I can say switchable rather than a photo switchable. For example, if a pH 7 is inactive in a particular system, AMP loaded nanocarriers, and when your pH is reduced to acidic range, they change their structural thing and they become more active, just like active and inactive systems. So then they become more active, because individually they may not be acting, but when it becomes a clumping or becoming a more compactness, and their entire charge is deferred. Charge is just like, you can see that there is a minus charges in entire places, but when they become more and more compact, you can see the plus charge is outside, and like that. There is a UV visible light, biologically active or inactive forms, also photosexual building blocks also there. So like that, leaching antimicrobial polymers also one can use it as some physiological chemical effects, which can cover the wherever the leachate is taking place, and then you can use the systems. There are some non-structured antimicrobials also there, especially they are the I can call it as a nano-based more things. As you know that nanoparticles with this size dependent variation in properties, and as the size structure changes, their performance changes, properties changes, processing changes. And if you use along with these polymers, their properties entirely different. And with the use of these systems, one can regenerate medicines, bio devices and sensing and wound dressing, which can be helping in this one. And you can also use them as a drug gene delivery, contact lenses, and bioassays, especially adhesive gels, one can use it. And microfabricated structures, one can look at the pre-polymer solution and patterning structure. With the patterning structure, one can look at this one. And they can also work as the stimuli responses and mechanically tough, hence they can be very detective in the system. Even nowadays, people are working in cancer treatment also, and nanoparticles with the system. And there are conjugated antimicrobials, where an natural compound is taken, and they can put one can look normal compound, you can take a barbitric acid, and you can add to this one antifungal system or antimicrobial system or a sedative system, hypotonic system, antibacterial system, and then they are very good source for the new antibiotics. And there are some other systems are there, when you introduce together, they become suppose for example, we can say this linker. When you give this linker to the hydrogel or what we call a emulsion-based system or a hydrogel-based system. Then when you introduce the polymers into the system, this micellar system, then they become a low active. If you remove then one high active, so while introducing you can give it this one, and when the site delivery system, one can develop a mechanism to remove these systems, either by changing the pH or by changing the what we call a ionotonic system solution, and then that will work in the system. And CRISPR and Cas antimicrobials also developing is a new way of looking at that, where you can break the gene and introduce the novel gene, which CRISPR system, and then develop the new system of this. And this is the mechanism where we can use it. And novel source mediated microorganisms are presently a lot of research is going on in developed countries in these things. So actinomycetes are going to be a rich source for antimicrobials, several antimicrobials. And one also look at other bacteria and fungal and synthetic systems. And one can use the uncultural bacteria, where we don't know what is the stress needed to produce the antimicrobials, or and what are the growth factors you don't know what is the common nutrients, what is the catalase related systems are, these systems, isolation of uncultivable bacteria. There is a lot of research, and recently there is a new methodology has been developed, and we are working in our laboratory to isolate the uncultivable bacteria, and we have isolated also. And the subsequent my research is in this direction only during this talk. And their environment, you can take it or a metagenomic approach, and then antimicrobial product test, and then look for the PCR, and then the bioinformatics system also one can look at this. So there is a peptide antibiotics also, still bioactive peptide widespread in the biological system. So antibiotics, then peptides together, you can put it and then walk it as a new antimicrobial things, which can be antimicrobial peptide or cell penetrating peptide or membrane active peptides. And these you can look at the effective of the multi-drug resistant organisms, especially for this one. And they can have improved pharmacokinetics and less toxicity, more stability. And the new term is coming, the streptogramines. This is nothing but a natural cyclic peptide antibiotics produced by certain subspecies of the streptomyces, and they are structurally related to macrolides and licosomides, but they differ and their activity is completely different with the system. This was I was saying about the antimicrobial natural products. If you look at 1990, first synthetic analysis of the antibiotic by soil bacteria was developed. 1910, salvacin is no longer in clinical use. First, this is a synthetic antibiotic used clinically. First report of the antibiosis by actinomycetes and penicillin, sulfonylamides. And this you can have at 1940s, there are spectrum of the things have come, and 1950, 1960, you can see the lot of, and this is called a golden era of the golden age of the antibiotics for this one. And you can see 1970, 60 to 7 or 65 to 70, you have only one antibiotic. 1980, only 2 or 3 are there, and there is a gap for the 2000, you have another 3 antibiotics, and 2010 this is the coming, and these are the synthetic systems are there. No natural antibiotic from 1970 to 2010 or 2020 till now. And if you look at the resistant development, if the 1928 one is antibiotic penicillin is developed, if you have a 1940, there is around 12 years. And if you look at the 1948 tetracyclines, and you have a macrolides, and within 2 years it is developed. resistance is developed. If you look at the carbapenems, you have a 1993. Like that, there is a macrolides, you have a 1985. So last 30 years, there is no new class of antibiotics are introduced in the system. That's why worldwide people are looking for the microbial systems and for a novel microbial systems, either metagenomic based or uncultivable based or a marine system or virgin systems. Everybody is looking for the system. So this is the one which we have used recently. This is a 2015 paper where they have used a specific growth factors for iron chelating siderophores development, and they have developed called iChip. iChip is the isolation chip, that is nothing but and based on this they can get the new uncultivable microbes, isolation of uncultivable microbials. They introduce first this chip into the soil and then introduce for the 30 days or 40 days with the system, and then there is a filter paper inside it, and then take the filter paper and that one again you spread into the system and then develop an individual colony. Either you use it as a normal isolation followed by checking it, or a specific antibiotic producing microorganism using a selective media and other thing, and you can follow the serial dilution and then do it. This is the one, and in that context we have developed the uncultivable system we have taken, and we have introduced in the plate and then develop the colonies and check it for the antimicrobial activity, and you can see the TLC running, and then we have done a crude extract showing the antibiotic. There is a 3 to 4 fractions. Each fraction were again tested for the antimicrobial activity and against the 2 microorganisms, and used the preparative TLC for the preparing the bulk compound isolation, and that compound is characterized by the different system and antibiotic is followed. Before that, what we want to know is that one, whether the isolated microorganism is a pathogenic or not. For this, we need to identify properly and use the Burki's manual methodology for doing this one. Since it is actinomycetes strain, there is a international streptomyces medias are there. ISP 1, 2, 3, 4 like that are there. Actinomycetes are specifically characterized with a particular media based, and there are international standards are there. For that one we have developed, and each media the colony morphology is changing it. That is the specificity of the actinomycetes. And we have developed the phylogenetic analysis based on the ribotyping, and we could able to see that one our organism is a streptomyces species, and this showed a similarity with the streptomyces species 1634M from this one, and we this is our microorganism, and we have deposited in the genome bank, and then we have looked in. Another one is a Pseudomonas curicosensis, and this is a, we call it as a ISD RAB19. This is RAB12, and the strain identification, based on that strain identification we have done it, and then growth curve and other things is a common system where it will grow particularly with the temperature, pH, and then we looked at the what is the media essential, how the RPM and other things, and how the growth curve is taking place, and what is the yield of the compound. RAB12 is giving a 120 mg per liter, whereas 95 mg per liter is a RAB19. And then we have developed the preparative HPLC, as I told you, this the characterization and other things, filtration, elution filtration, and antibiotic testing. That is called activity guided separation. We have done it. And then for the characterization, the previous talk by the Dr. N. Shankaraya has given a specific, elaborate lecture on the compound characterization. We have used the same techniques for that one, and we have initially used the MALDI-TOF for the molecular weight and HRMS, and then followed by the other FTIR or NMR or SCOSY, NOSY, and elemental analysis for the identification of the system. And based on this, we identified the organism or the compound, that is the RSP1, RSP2. And you know that one, when we looked at these two systems with the literature, it is belongs to the actinomycetin D, and which is nowhere there is a much difference except this proline ring. This is a keto group for RSP1, OH group for the RSP2. So what is the new with this one? When we looked at the all antimicrobial profile of this one, and you can see that RSP1 and RSP2 anti-actinomycetin D, since it is actinomycetin D analog, and we have looked at the mecananchol for the Candida species. And if you look at this RSP1 or RSP2, see the zone of inhibition is 35 and 32, whereas actinomycetin G is 25. And if you look at the M. luticus, Micrococcus luticus, 38, 38, 28. And this is 15, 14, 20. This is nothing. 37, 38, 30, 38, 35, 30, 40, 38, 32. So that almost all tested microorganisms under laboratory conditions is the isolated compounds are more effective than the actinomycetin D, which is our compound is just analog. There is a slight variation in the proline region. And even if you look at MIC values, 0.007 with this one, if you look at this one, 0.062, almost all 100 times more effective, or 10 times more effective on this one. And MBC values also 0.15, 1.124. Even if you look at the same microlyticus, also same thing, almost all they listen. Like that, we can say that with our isolated my compounds are more effective when compared to the actinomycetin D, and this variation is associated with the only simple modification of the either keto group at this position or OH group at this position. See, the variation of the particular ketone group has made it a more potent when compared to the natural things. And this paper has been published very well, and then it was a news item also with the Hindu news item as given in a daily paper, and there was a lot of queries for that one. And the getting the compound is not only the one part of a study. And its improvement and production, more production is associated studies are the another part of the study, because unless you get a 120 mg is not going to help us anything. Of course, if it is more effective, 120 mg also is very effective, one can look at that one. But we looked at the Plackett-Bowman design for using the same conditions which we are using one at a time, and then we changed the Plackett-Bowman design. According to the Plackett-Bowman design, we modeled our study and we studied, and there is each factor has certain influences. And if you look at the certain factors, only 3 to out of 7 factors, only 4 factors are significant in production of the antimicrobial compound. And keeping that one into consideration, central component design was developed or used for the only that 4 components which are significant in the system, and then we have produced it, and one at a time system, you have got a 28 mg if you are getting a 28 things, and a PBD design 36, and then CCD design 41. And initially we got only 120 mg and 12, that means 12 mg per 100 ml. And if one at a time optimization process 28 mg per 100 ml, and PBD design 36 and CCD design 41. So this is the 12 to 48 approximately 3.5-fold increase we could get able to get it. And what is the how it is can be used in industrially, we thought that because actinomycin D cannot be given just like that as a orally. If you want to give a orally or some administration related systems, we are used silica based material, where in this also the silica gel immobilized this antimicrobial system. Whatever we have developed compound, we are given 4 types of silica based hydrogels we have prepared, and then this is the preparation process we used it for that one. And then we looked at the what is the NMR out of it, how it is FTIR and other things are giving FTIR and UV spectra and antibacterial profile, how much it is there. And we could see it antibacterial profile upon 1 day, 2nd day, 3rd day, even 3rd day also it is slowly releasing. That is called a sustainable release of the system. And then we checked it the antimicrobial activity using this sol gel systems, and within 24 hours and 48 hours and 72 hours, if you have Pseudomonas aeruginosa and Salmonella typhi, Micrococcus luteus, and you can see up to 72 hours also it is showing the function. And then we looked at the structural characterization of the pure compounds, which I have mentioned this. This is a HRMS which we have used, and this is a carbon, nitrogen, hydrogen, oxygen percentages. And this is a FTIR system where how we have used it. This is a structural solution and ultra violet UV spectra and proton NMR, which was clearly told that 62 carbons were there, and the tentative positions also we have calculated. And RSP1 has 84 protons and 8 doublets, 1 triplet and 1 multiplet. And you have used heteronuclear spectra, COSI, NOSI, HMBC, HSQC, TOSI, and all these things we have used. Based on this, we have studied the structure and elucidated the structure. And nowadays people say that with NMR one can look at the structure, but I feel that one confirmation requires a lot of studies unless we know that one. And then bioactivity of the profile, anyway I have given it this one. And cytotoxicity also we have studied cytotoxicity, because actinomycin D is a more cytotoxic. That's why this actinomycin D is given only cancer patients when it is a critical stage. And then we have looked at the RSP1 and RSP02 values, and we have used different cells. And actinomycin as doxorubin, we have taken it. You can see that killing nature and other things, and it is working very well when compared to the actinomycin D or doxorubin. Doxorubin is again we have taken it, and then it works much effective when compared to this one. So then I can say success is the one has to look at that one, and you try. Of course, try is always is going to give initially fail, but try and fail, but never fail to try. This is, however, one should not be hindering like this, and one can looking at the front side one and outside one, and one can imagine to the things. And if you imagine properly, if you work properly, if you think properly, you can think any nasty thing, and which can be a reality if you try and try. So I can say that the scientific day should begin with the rising sun rather than a ending sun. Thank you very much.
Sir, thank you so much, sir. Thank you for the extraordinary presentation that you gave, sir. It was simple yet extraordinary, profound and effective, sir. I especially loved how you made the section so interesting. Thank you so much for your valuable time, sir. And now I can request Dr. Swarnalata Madam to proceed forward.
Any questions are there?
No questions, sir. We had not received any questions from audience side.
So audience are there or not?
Yeah, sir, there are there, sir.
Okay, anything?
Very nice presentation, sir. Now, vote of thanks I hand over to the principal, sir.
Good afternoon to all delegates, our eminent speakers, and faculty of our college. I thank Dr. N. Shankaraya Garu and Dr. R.S. Prakasham Garu, who are eminent speakers, for accepted our request immediately and given a lecture in webinar. Thank you, sir. So it was a great enlightening session for all students who attended the webinar. It was very informative session. All the faculty who attended it, on behalf of the management, faculty, and students of Mahathi College of Pharmacy, I express my gratitude towards learned speak for sharing the words of the wisdom and igniting the minds of enthusiastic participants. I also sincerely express my heartfelt thanks to all the principals, professors, associate professors, assistant professors, industry researchers, other professionals who have registered their names and participated in the webinar. I hereby acknowledge the enthusiastic participation I believe that the webinar has contributed in acquiring knowledge by participants from Himachal Pradesh to Kerala and from Rajasthan on west to Sikkim on east. Once again, I extend my heartfelt thanks to our speakers, management and faculty of Mahathi College of Pharmacy who took effort in making this webinar a grand success. I thank all the 1,700 delegates who attended this seminar, made this webinar a grand success. We hope we from the Mahathi College of Pharmacy extend our warm wishes to you all. Stay home, stay safe.
Okay, Syed, can I disconnect it?
Sir, of course, sir. You can disconnect it, sir. Thank you so much, sir, for
Welcome.
providing us your valuable time.
Okay.
Thank you so much, sir.
Okay, thank you,
Shankaraya,
Swarnalata.
sir, thank you so much, sir, for valuable section towards us. Thank you so much, sir.
Thank you.
And
Thank you.
Swarnalata-
Thank you. I wish you all the best.
Sir?
Thank you, thank you. Yes, tell me.
Yeah, sir. We
Anything?
can disconnect. Nothing else, sir. Thank you, sir.
Okay. You from your remote computer from your side?
Yes, I had removed that. No issues, sir, from this.
No issues. Okay.
Okay, sir.
Okay, all the best.
Thank you, sir. Thank you so much, sir.
Lata, for giving me opportunity in this case.
Thank you, sir. Thank you very much, sir, for your gracious.
Okay, okay, bye.
Okay, bye. So, a kind information for all the delegates who had been got registered. So, we are scrutinizing the visitors who have been a participant from the starting of the section. So, we are listing out the candidates who are attended from the starting of the sections. So, we will send you an personal emails with feedback forms. You just fill it out the feedback forms, and later you will get an certificate within the fraction of 4 to 5 days. So stay tuning to www.mcpm.edu.in website for regular updates about the feedback forms and next webinars. Thank you so much. So you can check the website link in the banner which is available straight below the screen. So if you have any queries related to that, you can WhatsApp us on related numbers which have been present in the website itself, or you can raise the queries in Facebook, which is available in website itself. So for any queries, you just visit to our website and you will find it out. Once again, I was displaying you the website links. You just copy those things. So this is our website link. You just go save it out and you can raise the queries in Facebook or else WhatsApp. Thank you so much. So now we are going to end this section. Thank you for participation.